Hello everyone, welcome to my stream. My apologies for having to use the text-to-speech voice. I couldn't get anything to work, so my apologies if this is boring and it slows me down a bit. But I've got some news to talk about today. Aliens are real. Aliens have more or less been confirmed in an official government setting. There's a hearing on UFOs. The people talking at the hearing have more or less confirmed the existence. We must make first contact. So yes, aliens are pretty much real. I hope we get to meet them soon. But considering the government considers aliens to be a threat in movies, I'm guessing we'll be forced to greet them with hostility. And we will never meet any aliens. So in an essence, we are truly alone. We are alone because the government doesn't want us to meet any aliens. Am I being too conspiracy-brained here? Maybe I am. I feel like a kid all over again. Granted, I was a kid a long time ago. I grew up with music and movies from the 1970s and 1980s. A good number of them involved aliens. Maybe they're actually true? Aliens are real. Aliens are real. Aliens are real. I wouldn't be surprised at this point if episodes of The X-Files are based on real stories of alien abductions. Are aliens real? ChatGPT. As of my last update in September 2021, there is no concrete scientific evidence confirming the existence of extraterrestrial life.
Are aliens real? ChatGPT. As of my last update in September 2021, there is no concrete scientific evidence confirming the existence of extraterrestrial life, commonly referred to as aliens. However, the universe is vast, with billions of galaxies, each containing billions of stars and potentially habitable planets. Given the sheer number of planets in the habitable zone of their stars, it is considered statistically likely that some form of extraterrestrial life may exist somewhere in the universe. Scientists and astronomers continue to search for signs of life beyond Earth using various methods, such as studying exoplanets for potential habitability and searching for signals from intelligent civilizations. The search for extraterrestrial life remains an active area of research, and future discoveries may shed more light on this intriguing question. Until conclusive evidence is found, the existence of aliens remains speculative and subject to ongoing exploration and investigation. What is the Fermi paradox? ChatGPT. The Fermi paradox is a thought-provoking question about the apparent contradiction between the high probability of extraterrestrial life existing in the universe and the lack of evidence or contact with advanced civilizations. The paradox is named after the Italian-American physicist Enrico Fermi, who reportedly asked the question "Where is everybody?" during a conversation about the possibility of extraterrestrial civilizations. The fundamental idea behind the Fermi paradox is as follows: the vastness of the universe. The observable universe contains billions of galaxies, each with billions of stars, many of which have planets orbiting them. With such an enormous number of potential habitable planets, the probability of Earth-like conditions occurring elsewhere is high. The potential for advanced civilizations, given the vast age of the universe, approximately 13.8 billion years, it is reasonable to assume that some civilizations might have developed advanced technology long before humanity did. Some of these civilizations could have even achieved interstellar travel or communication. Lack of evidence. Despite the high probability of other civilizations, we have not observed any clear evidence of their existence. There have been no confirmed signals from intelligent extraterrestrial beings, no sightings of spacecraft, and no other indications of their presence. Various proposed solutions and explanations have been suggested to address the Fermi paradox, rare Earth hypothesis. Some argue that Earth-like conditions are exceptionally rare, and Earth's unique characteristics allowed complex life to evolve. This would make advanced civilizations much rarer than initially assumed. Great filter theory. This idea suggests that there is some significant obstacle or filter that prevents civilizations from advancing beyond a certain point, such as self-destruction or other existential threats. Zoo hypothesis. According to this hypothesis, advanced civilizations are aware of Earth's existence but choose not to reveal themselves to us, perhaps out of a desire to avoid interference or to observe us without influence. The possibility of a cosmic noisy phase. It's conceivable that other civilizations have communicated or sent signals, but we have not detected them due to the vastness of space or limitations in our technology. The Fermi paradox remains a subject of active debate and speculation among scientists, researchers, and the general public, and it continues to fuel curiosity about the possibility of extraterrestrial life and our place in the universe. Is there life on other planets? ChatGPT. As of my last update in September 2021, there is currently no direct evidence confirming the existence of life on other planets. However, the search for extraterrestrial life is an active and ongoing area of scientific exploration. The vastness of the universe and the discovery of thousands of exoplanets, planets outside our solar system, have led many scientists to believe that the conditions necessary for life might be present on some of these distant worlds. Some key points to consider in the search for extraterrestrial life. Habitability. Scientists focus on identifying exoplanets located in the habitable zone around their host stars. The habitable zone is the region where conditions might be suitable for liquid water to exist on the planet's surface, a crucial factor for the development of life as we know it. Astrobiology. The field of astrobiology explores the potential for life beyond Earth. Researchers study extreme environments on our own planet that were once thought to be inhospitable but have since been found to host life. This knowledge informs the search for life in similar environments on other planets or moons. Extremophiles. Earth is home to extremophiles, microorganisms that thrive in extreme conditions, such as deep ocean vents, acidic environments, or extreme temperatures. Discovering life in such environments on Earth raises the possibility of similar life forms existing on other planets with comparable conditions. SETI, the search for extraterrestrial intelligence. SETI involves listening for artificial signals or communication from advanced civilizations in space. While no conclusive signals have been detected to date, SETI continues its efforts to monitor radio signals from space. Future missions. Several space missions, like NASA's James Webb Space Telescope and upcoming missions to Mars and other celestial bodies, aim to study and search for signs of life on other planets. It's essential to remain open to new discoveries and scientific advancements. As our technology and knowledge of the universe continue to expand, our understanding of the possibility of life beyond Earth may also evolve. Until concrete evidence is found, the question of whether life exists on other planets remains one of the most intriguing mysteries in science. What is quantum physics? ChatGPT quantum physics, also known as quantum mechanics, is a fundamental branch of physics that deals with the behavior of matter and energy at the smallest scales, such as atoms and subatomic particles. It provides a theoretical framework to describe the behavior of particles like electrons, photons, and other elementary particles, as well as their interactions with each other. At its core, quantum physics challenges our classical intuitions about the nature of reality, as it operates in a fundamentally different way than classical physics. Some key principles of quantum physics include wave-particle duality. One of the most fundamental concepts in quantum physics is the wave-particle duality. It suggests that particles, such as electrons or photons, can exhibit both particle-like behavior and wave-like behavior, depending on the experimental setup. Superposition. Quantum particles can exist in multiple states simultaneously, thanks to a phenomenon known as superposition. This means that until a measurement is made, a particle can exist in a combination of multiple possible states. Uncertainty principle, formulated by Werner Heisenberg, the uncertainty principle states that certain pairs of physical properties, such as a particle's position and momentum, cannot be precisely determined simultaneously. The more precisely we know one property, the less precisely we can know the other. Quantum entanglement. When two or more particles become entangled, their states become interconnected in such a way that the state of one particle is dependent on the state of the other, regardless of distance. This phenomenon has been experimentally verified and plays a significant role in quantum computing and quantum communication. Quantum tunneling. Quantum particles can tunnel through energy barriers that, according to classical physics, should be insurmountable. This phenomenon is crucial in understanding radioactive decay and various other processes. Quantum physics has far-reaching implications in various fields, including technology, information science, and cosmology. It has led to the development of technologies like transistors, lasers, and magnetic resonance imaging, MRI. Additionally, quantum computing aims to revolutionize computing power by harnessing quantum phenomena to perform complex calculations that would be practically impossible for classical computers. While quantum physics is highly successful in describing the behavior of particles at the quantum level, it does not fully align with our classical understanding of the world. This has led to ongoing debates and efforts to reconcile quantum mechanics with general relativity, the theory of gravity at cosmic scales. The search for a theory of everything that unifies quantum mechanics and general relativity is one of the most significant challenges in modern physics. Might humans be able to walk through portals one day to reach destinations far away? ChatGPT. As of my last knowledge update in September 2021, there is currently no scientific evidence or theoretical framework to suggest that humans will be able to walk through portals to reach destinations far away. The concept of portals, as commonly depicted in science fiction and fantasy, involves the existence of doorways or gateways that connect different locations or dimensions instantaneously. While the idea of portals is fascinating and captures the imagination, it remains purely speculative and fictional in the context of our current scientific understanding. In the real world, our understanding of physics, particularly within the realm of general relativity and quantum mechanics, does not support the existence of such portals. General relativity, which describes gravity and the large-scale structure of the universe, does allow for the existence of wormholes, which are theoretical shortcuts through space-time that could connect distant regions. However, the stability and practicality of traversable wormholes remain highly speculative and purely theoretical. There are significant challenges, such as the need for exotic matter with negative energy density, to keep a traversable wormhole open, which we currently have no experimental evidence for and may not even exist. Quantum mechanics, on the other hand, deals with the behavior of particles at very small scales, and it introduces intriguing phenomena like quantum entanglement and superposition. While these concepts have inspired ideas of teleportation in popular culture, they do not provide a basis for the creation of portals for human travel. In summary, while the concept of walking through portals is a fascinating and popular idea in fiction, there is currently no scientific evidence or established theory supporting the possibility of such portals in the real world. As our understanding of physics evolves and new discoveries are made, our perspectives on such ideas may change, but for now, they remain within the realm of science fiction and imagination. Would quantum tunneling allow humans to walk through portals to faraway places? ChatGPT. As of my last knowledge update in September 2021, quantum tunneling is a fascinating phenomenon in quantum mechanics that allows particles to pass through energy barriers that, according to classical physics, they should not be able to overcome. While quantum tunneling is a well-established and experimentally verified concept in the microscopic world of particles, it is important to understand that it does not enable macroscopic objects, such as humans, to walk through portals to faraway places. Quantum tunneling operates at the quantum scale, involving individual particles like electrons and photons. It occurs under specific conditions and is typically relevant to extremely tiny particles moving through energy barriers on the order of nanometers. For macroscopic objects like humans, the principles of quantum mechanics do not manifest in the same way as they do for subatomic particles. The energy barriers that would need to be overcome for a macroscopic object to tunnel through space on a human scale are astronomically high and currently beyond the capabilities of our technology and understanding of physics. Furthermore, even if quantum tunneling were applicable to larger objects, it would not create the kind of portal seen in science fiction and fantasy. Quantum tunneling is a probabilistic phenomenon that involves the behavior of individual particles. It does not provide a mechanism for the creation of stable, traversable portals that would allow humans to transport themselves over long distances. In summary, while quantum tunneling is a remarkable phenomenon that challenges our classical understanding of physics, it does not enable humans to walk through portals to faraway places as depicted in fiction. The concept of such portals remains within the realm of imagination and science fiction rather than established scientific theory. Would it be possible to shrink a person down to the size of particles and enter a quantum realm to quantum tunnel to faraway places and then return to normal size to explore the place they've traveled to? ChatGPT. As of my last knowledge update in September 2021, the concept of shrinking a person down to the size of particles and allowing them to enter a quantum realm for the purpose of quantum tunneling to faraway places is purely speculative and belongs to the realm of science fiction. Quantum tunneling is a phenomenon that occurs at the quantum scale, involving individual particles like electrons. It is a probabilistic effect that allows particles to pass through energy barriers that, according to classical physics, they should not be able to overcome. However, quantum tunneling is not a mechanism for teleportation or instantaneous travel to faraway places. The idea of shrinking a person to the size of particles raises numerous scientific challenges and contradictions. At the quantum scale, the behavior of matter and energy is governed by the laws of quantum mechanics, which are vastly different from the classical physics that describe the behavior of macroscopic objects like humans. The principles of quantum mechanics are fundamentally different from those of classical physics and do not readily apply to macroscopic objects. Additionally, even if we were to imagine a way to shrink a person to the quantum scale, the notion of navigating or exploring a quantum realm is highly speculative. At the quantum level, particles do not have well-defined positions or trajectories in the way that macroscopic objects do. The concept of a person navigating through a quantum realm in a controlled manner is currently beyond the scope of our understanding of physics. It's important to remember that scientific theories and concepts are based on empirical evidence, experimentation, and mathematical models. As of now, there is no scientific evidence to support the idea of shrinking a person to the quantum scale for travel or exploration. While science fiction may explore imaginative ideas like these, they remain in the realm of fiction until supported by scientific evidence and theoretical frameworks. Contents Hide, Top, Overview and Fundamental Concepts Mathematical Formulation Toggle Mathematical Formulation Subsection Uncertainty Principle Composite Systems and Entanglement Equivalence between Formulations Symmetries and Conservation Laws Examples Toggle Examples Subsection Free Particle Particle in a Box Harmonic Oscillator Mach, Zender Interferometer Applications Relation to Other Scientific Theories Toggle Relation to Other Scientific Theories Subsection Classical Mechanics Special Relativity and Electrodynamics Relation to General Relativity Philosophical Implications History See also Explanatory Notes References Further reading External links Quantum Mechanics Article Talk Read View Source View History Tools from Wikipedia. The Free Encyclopedia, redirected from Quantum Physics, Quantum Realm redirects here. For the fictional location in the Marvel Cinematic Universe, see Quantum Realm. For a more accessible and less technical introduction to this topic, see Introduction to Quantum Mechanics. Wave functions of the electron in a hydrogen atom at different energy levels. Quantum mechanics cannot predict the exact location of a particle in space, only the probability of finding it at different locations. The brighter areas represent a higher probability of finding the electron. Part of a series of articles about quantum mechanics, Schrödinger equation Introduction Glossary History Background Fundamentals Experiments Formulations Equations Interpretations Advanced Topics Scientists Veit Quantum mechanics is a fundamental theory in physics that provides a description of the physical properties of nature at the scale of atoms and subatomic particles. 1.1 It is the foundation of all quantum physics including quantum chemistry, quantum field theory, quantum technology, and quantum information science. Classical physics, the collection of theories that existed before the advent of quantum mechanics, describes many aspects of nature at an ordinary, macroscopic, scale, but is not sufficient for describing them at small, atomic and subatomic, scales. Most theories in classical physics can be derived from quantum mechanics as an approximation valid at large, macroscopic, scale. 3 Quantum mechanics differs from classical physics in that energy, momentum, angular momentum, and other quantities of a bound system are restricted to discrete values. Quantization: objects have characteristics of both particles and waves, wave-particle duality, and there are limits to how accurately the value of a physical quantity can be predicted prior to its measurement, given a complete set of initial conditions, the uncertainty principle. Quantum mechanics arose gradually from theories to explain observations that could not be reconciled with classical physics, such as Max Planck's solution in 1900 to the blackbody radiation problem, and the correspondence between energy and frequency in Albert Einstein's 1905 paper, which explained the photoelectric effect. These early attempts to understand microscopic phenomena, now known as the old quantum theory, led to the full development of quantum mechanics in the mid-1920s by Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, Paul Dirac and others. The modern theory is formulated in various specially developed mathematical formalisms. In one of them, a mathematical entity called the wave function provides information, in the form of probability amplitudes, about what measurements of a particle's energy, momentum, and other physical properties may yield. Overview and fundamental concepts. Quantum mechanics allows the calculation of properties and behavior of physical systems. It is typically applied to microscopic systems, molecules, atoms, and subatomic particles. It has been demonstrated to hold for complex molecules with thousands of atoms but its application to human beings raises philosophical problems, such as Wigner's friend, and its application to the universe as a whole remains speculative. 5 Predictions of quantum mechanics have been verified experimentally to an extremely high degree of accuracy. Note 1 A fundamental feature of the theory is that it usually cannot predict with certainty what will happen, but only give probabilities. Mathematically, a probability is found by taking the square of the absolute value of a complex number, known as a probability amplitude. This is known as the Born rule, named after physicist Max Born. For example, a quantum particle like an electron can be described by a wave function, which associates to each point in space a probability amplitude. Applying the Born rule to these amplitudes gives a probability density function for the position that the electron will be found to have when an experiment is performed to measure it. This is the best the theory can do. It cannot say for certain where the electron will be found. The Schrödinger equation relates the collection of probability amplitudes that pertain to one moment of time to the collection of probability amplitudes that pertain to another. One consequence of the mathematical rules of quantum mechanics is a trade-off in predictability between different measurable quantities. The most famous form of this uncertainty principle says that no matter how a quantum particle is prepared or how carefully experiments upon it are arranged, it is impossible to have a precise prediction for a measurement of its position and also at the same time for a measurement of its momentum. Another consequence of the mathematical rules of quantum mechanics is the phenomenon of quantum interference, which is often illustrated with the double-slit experiment. In the basic version of this experiment, a coherent light source, such as a laser beam, illuminates a plate pierced by 2 parallel slits, and the light passing through the slits is observed on a screen behind the plate. 6, 102 to 111 to 1.1 to 1.8 The wave nature of light causes the light waves passing through the 2 slits to interfere, producing bright and dark bands on the screen, a result that would not be expected if light consisted of classical particles. 6 However, the light is always found to be absorbed at the screen at discrete points, as individual particles rather than waves. The interference pattern appears via the varying density of these particle hits on the screen. Furthermore, versions of the experiment that include detectors at the slits find that each detected photon passes through one slit, as would a classical particle, and not through both slits, as would a wave. 6, 109.78 However, such experiments demonstrate that particles do not form the interference pattern if one detects which slit they pass through. Other atomic scale entities, such as electrons, are found to exhibit the same behavior when fired towards a double slit. This behavior is known as wave-particle duality. Another counterintuitive phenomenon predicted by quantum mechanics is quantum tunneling. A particle that goes up against a potential barrier can cross it, even if its kinetic energy is smaller than the maximum of the potential 9 in classical mechanics. This particle would be trapped. Quantum tunneling has several important consequences, enabling radioactive decay, nuclear fusion in stars, and applications such as scanning tunneling microscopy and the tunnel diode 10. When quantum systems interact, the result can be the creation of quantum entanglement. Their properties become so intertwined that a description of the whole solely in terms of the individual parts is no longer possible. Erwin Schrödinger called entanglement the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. 11 Quantum entanglement enables the counterintuitive properties of quantum pseudo-telepathy, and can be a valuable resource in communication protocols, such as quantum key distribution and superdense coding. 12 Contrary to popular misconception, entanglement does not allow sending signals faster than light, as demonstrated by the no communication theorem. 12 Another possibility opened by entanglement is testing for hidden variables, hypothetical properties more fundamental than the quantities addressed in quantum theory itself, knowledge of which would allow more exact predictions than quantum theory can provide. A collection of results, most significantly Bell's theorem, have demonstrated that broad classes of such hidden variable theories are in fact incompatible with quantum physics. According to Bell's theorem, if nature actually operates in accord with any theory of local hidden variables, then the results of a Bell test will be constrained in a particular, quantifiable way. Many Bell tests have been performed, using entangled particles, and they have shown results incompatible with the constraints imposed by local hidden variables. 13-14 It is not possible to present these concepts in more than a superficial way without introducing the actual mathematics involved. Understanding quantum mechanics requires not only manipulating complex numbers, but also linear algebra, differential equations, group theory, and other more advanced subjects. Note 2 accordingly. This article will present a mathematical formulation of quantum mechanics and survey its application to some useful and oft-studied examples. Mathematical formulation. Main article, Mathematical formulation of quantum mechanics. In the mathematically rigorous formulation of quantum mechanics, the state of a quantum mechanical system is a vector belonging to a separable, complex Hilbert space. This vector is postulated to be normalized under the Hilbert space inner product, that is, it obeys, equals 1, and it is well defined up to a complex number of modulus 1, the global phase, that is, and represent the same physical system. In other words, the possible states are points in the projective space of a Hilbert space, usually called the complex projective space. The exact nature of this Hilbert space is dependent on the system. For example, for describing position and momentum, the Hilbert space is the space of complex square integrable functions 2, while the Hilbert space for the spin of a single proton is simply the space of two-dimensional complex vectors 2 with the usual inner product. Physical quantities of interest, position, momentum, energy, spin, are represented by observables, which are Hermitian, more precisely, self-adjoint, linear operators acting on the Hilbert space. A quantum state can be an eigenvector of an observable, in which case it is called an eigenstate, and the associated eigenvalue corresponds to the value of the observable in that eigenstate. More generally, a quantum state will be a linear combination of the eigenstates, known as a quantum superposition. When an observable is measured, the result will be one of its eigenvalues with probability given by the Born rule. In the simplest case, the eigenvalue is non-degenerate and the probability is given by rightward arrow, 2, where rightward arrow is its associated eigenvector. More generally, the eigenvalue is degenerate and the probability is given by, where is the projector onto its associated eigenspace. In the continuous case, these formulas give instead the probability density. After the measurement, if result was obtained, the quantum state is postulated to collapse to rightward arrow, in the non-degenerate case, or to slash, in the general case. The probabilistic nature of quantum mechanics thus stems from the act of measurement. This is one of the most difficult aspects of quantum systems to understand. It was the central topic in the famous Bohr-Einstein debates, in which the two scientists attempted to clarify these fundamental principles by way of thought experiments. In the decades after the formulation of quantum mechanics, the question of what constitutes a measurement has been extensively studied. Newer interpretations of quantum mechanics have been formulated that do away with the concept of wave function collapse, see, for example, the many worlds interpretation. The basic idea is that when a quantum system interacts with a measuring apparatus, their respective wave functions become entangled so that the original quantum system ceases to exist as an independent entity. For details, see the article on measurement in quantum mechanics 17. The time evolution of a quantum state is described by the Schrödinger equation, equals. Here denotes the Hamiltonian, the observable corresponding to the total energy of the system, and is the reduced Planck constant. The constant is introduced so that the Hamiltonian is reduced to the classical Hamiltonian in cases where the quantum system can be approximated by a classical system. The ability to make such an approximation in certain limits is called the correspondence principle. The solution of this differential equation is given by =0. The operator =/ is known as the time evolution operator, and has the crucial property that it is unitary. This time evolution is deterministic in the sense that, given an initial quantum state, 0, it makes a definite prediction of what the quantum state will be at any later time. 18 Fig. 1. Probability densities corresponding to the wave functions of an electron in a hydrogen atom possessing definite energy levels, increasing from the top of the image to the bottom, n equals 1, 2, 3, and angular momenta, increasing across from left to right, s, p, d. Denser areas correspond to higher probability density in a position measurement. Such wave functions are directly comparable to Chladni's figures of acoustic modes of vibration in classical physics and are modes of oscillation as well, possessing a sharp energy and thus, a definite frequency. The angular momentum and energy are quantized and take only discrete values like those shown. As is the case for resonant frequencies in acoustics. Some wave functions produce probability distributions that are independent of time, such as eigenstates of the Hamiltonian. Many systems that are treated dynamically in classical mechanics are described by such static wave functions. For example, a single electron in an unexcited atom is pictured classically as a particle moving in a circular trajectory around the atomic nucleus, whereas in quantum mechanics, it is described by a static wave function surrounding the nucleus. For example, the electron wave function for an unexcited hydrogen atom is a spherically symmetric function known as an s orbital, Fig. 1. Analytic solutions of the Schrödinger equation are known for very few relatively simple model Hamiltonians, including the quantum harmonic oscillator, the particle in a box, the dihydrogen cation, and the hydrogen atom. Even the helium atom, which contains just 2 electrons, has defied all attempts at a fully analytic treatment. However, there are techniques for finding approximate solutions. One method, called perturbation theory, uses the analytic result for a simple quantum mechanical model to create a result for a related but more complicated model by, for example, the addition of a weak potential energy. Another method is called semi-classical equation of motion, which applies to systems for which quantum mechanics produces only small deviations from classical behavior. These deviations can then be computed based on the classical motion. This approach is particularly important in the field of quantum chaos. Uncertainty principle. One consequence of the basic quantum formalism is the uncertainty principle. In its most familiar form, this states that no preparation of a quantum particle can imply simultaneously precise predictions both for a measurement of its position and for a measurement of its momentum. 1920 Both position and momentum are observables, meaning that they are represented by Hermitian operators. The position operator and momentum operator do not commute, but rather satisfy the canonical commutation relation, equals. Given a quantum state, the Born rule lets us compute expectation values for both and moreover for powers of them. Defining the uncertainty for an observable by a standard deviation, we have equals 2, and likewise for the momentum, equals 2. The uncertainty principle states that greater than or equal to 2. Either standard deviation can in principle be made arbitrarily small, but not both simultaneously. 21 This inequality generalizes to arbitrary pairs of self-adjoint operators, and the commutator of these two operators is equals, and this provides the lower bound on the product of standard deviations, greater than or equal to 1 2. Another consequence of the canonical commutation relation is that the position and momentum operators are Fourier transforms of each other, so that a description of an object according to its momentum is the Fourier transform of its description according to its position. The fact that dependence in momentum is the Fourier transform of the dependence in position means that the momentum operator is equivalent, up to n/factor, to taking the derivative according to the position, since in Fourier analysis differentiation corresponds to multiplication in the dual space. This is why in quantum equations in position space, the momentum is replaced by, and in particular in the non-relativistic Schrödinger equation in position space, the momentum squared term is replaced with a Laplacian times 219 composite systems and entanglement when two different quantum systems are considered together. The Hilbert space of the combined system is the tensor product of the Hilbert spaces of the two components. For example, let A and B be two quantum systems, with Hilbert spaces and, respectively. The Hilbert space of the composite system is then equals. If the state for the first system is the vector and the state for the second system is, then the state of the composite system is. Not all states in the joint Hilbert space can be written in this form, however, because the superposition principle implies that linear combinations of these separable or product states are also valid. For example, if and are both possible states for system, and likewise and are both possible states for system, then 1 2 plus is a valid joint state that is not separable. States that are not separable are called entangled. 22-23 If the state for a composite system is entangled, it is impossible to describe either component system A or system B by a state vector. One can instead define reduced density matrices that describe the statistics that can be obtained by making measurements on either component system alone. This necessarily causes a loss of information, though, knowing the reduced density matrices of the individual systems is not enough to reconstruct the state of the composite system. 22-23 Just as density matrices specify the state of a subsystem of a larger system, analogously, positive operator valued measures, POVMs, describe the effect on a subsystem of a measurement performed on a larger system. POVMs are extensively used in quantum information theory. 22-24 As described above, entanglement is a key feature of models of measurement processes in which an apparatus becomes entangled with the system being measured. Systems interacting with the environment in which they reside generally become entangled with that environment, a phenomenon known as quantum decoherence. This can explain why, in practice, quantum effects are difficult to observe in systems larger than microscopic. 25 Equivalence between formulations. There are many mathematically equivalent formulations of quantum mechanics. One of the oldest and most common is the transformation theory proposed by Paul Dirac, which unifies and generalizes the two earliest formulations of quantum mechanics, matrix mechanics, invented by Werner Heisenberg, and wave mechanics, invented by Erwin Schrödinger. 26 An alternative formulation of quantum mechanics is Feynman's path integral formulation, in which a quantum mechanical amplitude is considered as a sum over all possible classical and non-classical paths between the initial and final states. This is the quantum mechanical counterpart of the action principle in classical mechanics. Symmetries and conservation laws. Main article, Noether's theorem. The Hamiltonian is known as the generator of time evolution, since it defines a unitary time evolution operator, equals / for each value of. From this relation between, and, it follows that any observable that commutes with will be conserved, its expectation value will not change over time. This statement generalizes, as mathematically, any Hermitian operator can generate a family of unitary operators parameterized by a variable. Under the evolution generated by, any observable that commutes with will be conserved. Moreover, if is conserved by evolution under, then is conserved under the evolution generated by. This implies a quantum version of the result proven by Emmy Noether in classical, Lagrangian, mechanics. For every differentiable symmetry of a Hamiltonian, there exists a corresponding conservation law. Examples: free particle main article, free particle position space probability density of a Gaussian wave packet moving in one dimension in free space. The simplest example of a quantum system with a position degree of freedom is a free particle in a single spatial dimension. A free particle is one which is not subject to external influences, so that its Hamiltonian consists only of its kinetic energy, equals 122 equals 2222. The general solution of the Schrödinger equation is given by equals 1 to indefinite integral infinity caret 0 22 d, which is a superposition of all possible plane waves 22, which are eigenstates of the momentum operator with momentum equals. The coefficients of the superposition are caret 0, which is the Fourier transform of the initial quantum state 0. It is not possible for the solution to be a single momentum eigenstate, or a single position eigenstate, as these are not normalizable quantum states. Note 3. Instead, we can consider a Gaussian wave packet, 0, equals 1422, which has Fourier transform, and therefore momentum distribution caret 0, equals 422. We see that as we make smaller, the spread in position gets smaller, but the spread in momentum gets larger. Conversely, by making larger we make the spread in momentum smaller, but the spread in position gets larger. This illustrates the uncertainty principle. As we let the Gaussian wave packet evolve in time, we see that its center moves through space at a constant velocity, like a classical particle with no forces acting on it. However, the wave packet will also spread out as time progresses, which means that the position becomes more and more uncertain. The uncertainty in momentum, however, stays constant. 27 Particle in a box, one-dimensional potential energy box, or infinite potential well, main article, particle in a box. The particle in a one-dimensional potential energy box is the most mathematically simple example where restraints lead to the quantization of energy levels. The box is defined as having zero potential energy everywhere inside a certain region, and therefore infinite potential energy everywhere outside that region. 1977-78 For the one-dimensional case in the direction, the time-independent Schrödinger equation may be written 2222 equals. With the differential operator defined by caret equals, the previous equation is evocative of the classic kinetic energy analog, 12 caret 2 equals, with state in this case having energy coincident with the kinetic energy of the particle. The general solutions of the Schrödinger equation for the particle in a box are, equals plus equals 222 or, from Euler's formula, equals sin, plus cos. The infinite potential walls of the box determine the values of, and at equals 0 and equals where must be 0. Thus, at equals 0, 0, equals 0 equals sin, 0, plus cos, 0, equals and equals 0. At equals 0 equals sin, in which cannot be 0 as this would conflict with the postulate that has norm 1. Therefore, since sin, equals 0, must be an integer multiple of, equals 1, 2, 3. This constraint on implies a constraint on the energy levels, yielding equals 22222 equals 2282. A finite potential well is the generalization of the infinite potential well problem to potential wells having finite depth. The finite potential well problem is mathematically more complicated than the infinite particle in a box problem, as the wave function is not pinned to 0 at the walls of the well. Instead, the wave function must satisfy more complicated mathematical boundary conditions, as it is non-zero in regions outside the well. Another related problem is that of the rectangular potential barrier, which furnishes a model for the quantum tunneling effect that plays an important role in the performance of modern technologies such as flash memory and scanning tunneling microscopy. Harmonic oscillator main article, quantum harmonic oscillator. Some trajectories of a harmonic oscillator, i.e. a ball attached to a spring, in classical mechanics, AB, and quantum mechanics, CH. In quantum mechanics, the position of the ball is represented by a wave, called the wave function, with the real part shown in blue and the imaginary part shown in red. Some of the trajectories, such as C, D, E, and F, are standing waves, or stationary states. Each standing wave frequency is proportional to a possible energy level of the oscillator. This energy quantization does not occur in classical physics, where the oscillator can have any energy. As in the classical case, the potential for the quantum harmonic oscillator is given by equals 1222. This problem can either be treated by directly solving the Schrödinger equation, which is not trivial, or by using the more elegant latter method first proposed by Paul Dirac. The eigenstates are given by equals 1 2. 1/422 equals 0, 1, 2. Where Hn are the Hermite polynomials, equals 1, 2, 2, and the corresponding energy levels are equals plus 1, 2. This is another example illustrating the discretization of energy for bound states. Mach, Zehnder interferometer. Schematic of a Mach, Zehnder interferometer. The Mach, Zehnder interferometer, MZI, illustrates the concepts of superposition and interference with linear algebra in dimension 2, rather than differential equations. It can be seen as a simplified version of the double-slit experiment, but it is of interest in its own right, for example in the delayed choice quantum eraser, the Elitzur, Vaidman-Baum tester, and in studies of quantum entanglement 28-29. We can model a photon going through the interferometer by considering that at each point it can be in a superposition of only two paths. The lower path, which starts from the left, goes straight through both beam splitters, and ends at the top, and the upper path, which starts from the bottom, goes straight through both beam splitters, and ends at the right. The quantum state of the photon is therefore a vector set membership symbol 2, that is a superposition of the lower path equals 1 0, and the upper path equals 0 1, that is, equals plus 4 complex. In order to respect the postulate that equals 1, we require that 2 plus 2 equals 1. Both beam splitters are modeled as the unitary matrix equals 1 2, 1 1, which means that when a photon meets the beam splitter it will either stay on the same path with a probability amplitude of 1/2, or be reflected to the other path with a probability amplitude of /2. The phase shifter on the upper arm is modeled as the unitary matrix equals 1 0 0 delta phi, which means that if the photon is on the upper path it will gain a relative phase of delta phi, and it will stay unchanged if it is in the lower path. A photon that enters the interferometer from the left will then be acted upon with a beam splitter, a phase shifter, and another beam splitter, and so end up in the state equals delta phi /2, sin, delta phi /2, cos, delta phi /2, and the probabilities that it will be detected at the right or at the top are given respectively by equals 2 equals cos 2 delta phi 2, equals 2 equals sin 2 delta phi 2. One can therefore use the Mach, Zehnder interferometer to estimate the phase shift by estimating these probabilities. It is interesting to consider what would happen if the photon were definitely in either the lower or upper paths between the beam splitters. This can be accomplished by blocking one of the paths, or equivalently by removing the first beam splitter, and feeding the photon from the left or the bottom, as desired. In both cases there will be no interference between the paths anymore, and the probabilities are given by equals 1/2, independently of the phase delta phi. From this we can conclude that the photon does not take one path or another after the first beam splitter, but rather that it is in a genuine quantum superposition of the two paths. 30 Applications. Main article, Applications of Quantum Mechanics. Quantum mechanics has had enormous success in explaining many of the features of our universe, with regards to small-scale and discrete quantities and interactions which cannot be explained by classical methods. Note: for quantum mechanics is often the only theory that can reveal the individual behaviors of the subatomic particles that make up all forms of matter, electrons, protons, neutrons, photons, and others. Solid-state physics and materials science are dependent upon quantum mechanics. 31 In many aspects modern technology operates at a scale where quantum effects are significant. Important applications of quantum theory include quantum chemistry, quantum optics, quantum computing, superconducting magnets, light-emitting diodes, the optical amplifier and the laser, the transistor, and semiconductors such as the microprocessor, medical and research imaging such as magnetic resonance imaging and electron microscopy. 32 Explanations for many biological and physical phenomena are rooted in the nature of the chemical bond, most notably the macromolecule DNA. Relation to other scientific theories. Modern physics equals plus lambda equals Schrödinger and Einstein field equations. Founders, concepts, branches, scientists, categories. Veit classical mechanics. The rules of quantum mechanics assert that the state space of a system is a Hilbert space and that observables of the system are Hermitian operators acting on vectors in that space, although they do not tell us which Hilbert space or which operators. These can be chosen appropriately in order to obtain a quantitative description of a quantum system, a necessary step in making physical predictions. An important guide for making these choices is the correspondence principle, a heuristic which states that the predictions of quantum mechanics reduce to those of classical mechanics in the regime of large quantum numbers. 33 One can also start from an established classical model of a particular system, and then try to guess the underlying quantum model that would give rise to the classical model in the correspondence limit. This approach is known as quantization. When quantum mechanics was originally formulated, it was applied to models whose correspondence limit was non-relativistic classical mechanics. For instance, the well-known model of the quantum harmonic oscillator uses an explicitly non-relativistic expression for the kinetic energy of the oscillator, and is thus a quantum version of the classical harmonic oscillator. Complications arise with chaotic systems, which do not have good quantum numbers, and quantum chaos studies the relationship between classical and quantum descriptions in these systems. Quantum decoherence is a mechanism through which quantum systems lose coherence, and thus become incapable of displaying many typically quantum effects. Quantum superpositions become simply probabilistic mixtures, and quantum entanglement becomes simply classical correlations. Quantum coherence is not typically evident at macroscopic scales, except maybe at temperatures approaching absolute zero, at which quantum behavior may manifest macroscopically. Note 5 Many macroscopic properties of a classical system are a direct consequence of the quantum behavior of its parts. For example, the stability of bulk matter, consisting of atoms and molecules which would quickly collapse under electric forces alone, the rigidity of solids, and the mechanical, thermal, chemical, optical, and magnetic properties of matter are all results of the interaction of electric charges under the rules of quantum mechanics. 34 Special relativity and electrodynamics. Early attempts to merge quantum mechanics with special relativity involved the replacement of the Schrödinger equation with a covariant equation such as the Klein-Gordon equation or the Dirac equation. While these theories were successful in explaining many experimental results, they had certain unsatisfactory qualities stemming from their neglect of the relativistic creation and annihilation of particles. A fully relativistic quantum theory required the development of quantum field theory, which applies quantization to a field, rather than a fixed set of particles. The first complete quantum field theory, quantum electrodynamics, provides a fully quantum description of the electromagnetic interaction. Quantum electrodynamics is, along with general relativity, one of the most accurate physical theories ever devised. 35-36 The full apparatus of quantum field theory is often unnecessary for describing electrodynamic systems. A simpler approach, one that has been used since the inception of quantum mechanics, is to treat charged particles as quantum mechanical objects being acted on by a classical electromagnetic field. For example, the elementary quantum model of the hydrogen atom describes the electric field of the hydrogen atom using a classical 2/40 Coulomb potential. This semi-classical approach fails if quantum fluctuations in the electromagnetic field play an important role, such as in the emission of photons by charged particles. Quantum field theories for the strong nuclear force and the weak nuclear force have also been developed. The quantum field theory of the strong nuclear force is called quantum chromodynamics, and describes the interactions of subnuclear particles such as quarks and gluons. The weak nuclear force and the electromagnetic force were unified, in their quantized forms, into a single quantum field theory, known as electroweak theory, by the physicists Abdus Salam, Sheldon Glashow, and Steven Weinberg. 37 Relation to general relativity. Even though the predictions of both quantum theory and general relativity have been supported by rigorous and repeated empirical evidence, their abstract formalisms contradict each other, and they have proven extremely difficult to incorporate into one consistent, cohesive model. Gravity is negligible in many areas of particle physics, so that unification between general relativity and quantum mechanics is not an urgent issue in those particular applications. However, the lack of a correct theory of quantum gravity is an important issue in physical cosmology and the search by physicists for an elegant theory of everything, too. Consequently, resolving the inconsistencies between both theories has been a major goal of 20th and 21st century physics. This TOE would combine not only the models of subatomic physics but also derive the four fundamental forces of nature from a single force or phenomenon. 38 One proposal for doing so is string theory, which posits that the point-like particles of particle physics are replaced by one-dimensional objects called strings. String theory describes how these strings propagate through space and interact with each other. On distance scales larger than the string scale, a string looks just like an ordinary particle, with its mass, charge, and other properties determined by the vibrational state of the string. In string theory, one of the many vibrational states of the string corresponds to the graviton, a quantum mechanical particle that carries gravitational force. 3940 Another popular theory is loop quantum gravity, LQG, which describes quantum properties of gravity and is thus a theory of quantum spacetime. LQG is an attempt to merge and adapt standard quantum mechanics and standard general relativity. This theory describes space as an extremely fine fabric woven of finite loops called spin networks. The evolution of a spin network over time is called a spin foam. The characteristic length scale of a spin foam is the Planck length, approximately 1.616 × 1035 m, and so lengths shorter than the Planck length are not physically meaningful in LQG. 41 Philosophical implications. Main article, Interpretations of Quantum Mechanics. Unsolved problem in physics. Is there a preferred interpretation of quantum mechanics? How does the quantum description of reality, which includes elements such as the superposition of states and wave function collapse, give rise to the reality we perceive? More unsolved problems in physics. Since its inception, the many counterintuitive aspects and results of quantum mechanics have provoked strong philosophical debates and many interpretations. The arguments center on the probabilistic nature of quantum mechanics, the difficulties with wave function collapse and the related measurement problem, and quantum non-locality. Perhaps the only consensus that exists about these issues is that there is no consensus. Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." 42 According to Steven Weinberg, there is now in my opinion no entirely satisfactory interpretation of quantum mechanics. 43 The views of Niels Bohr, Werner Heisenberg, and other physicists are often grouped together as the Copenhagen interpretation. 44-45 According to these views, the probabilistic nature of quantum mechanics is not a temporary feature which will eventually be replaced by a deterministic theory, but is instead a final renunciation of the classical idea of causality. Bohr in particular emphasized that any well-defined application of the quantum mechanical formalism must always make reference to the experimental arrangement, due to the complementary nature of evidence obtained under different experimental situations. Copenhagen-type interpretations remain popular in the 21st century. 46 Albert Einstein, himself one of the founders of quantum theory, was troubled by its apparent failure to respect some cherished metaphysical principles, such as determinism and locality. Einstein's long-running exchanges with Bohr about the meaning and status of quantum mechanics are now known as the Bohr-Einstein debates. Einstein believed that underlying quantum mechanics must be a theory that explicitly forbids action at a distance. He argued that quantum mechanics was incomplete, a theory that was valid but not fundamental, analogous to how thermodynamics is valid, but the fundamental theory behind it is statistical mechanics. In 1935, Einstein and his collaborators Boris Podolsky and Nathan Rosen published an argument that the principle of locality implies the incompleteness of quantum mechanics, a thought experiment later termed the Einstein-Podolsky-Rosen paradox. Note 6. In 1964, John Bell showed that Ypres' principle of locality, together with determinism, was actually incompatible with quantum mechanics. They implied constraints on the correlations produced by distance systems, now known as Bell inequalities, that can be violated by entangled particles. 51. Since then several experiments have been performed to obtain these correlations, with the result that they do in fact violate Bell inequalities, and thus falsify the conjunction of locality with determinism. 1314 Bohmian mechanics shows that it is possible to reformulate quantum mechanics to make it deterministic, at the price of making it explicitly non-local. It attributes not only a wave function to a physical system, but in addition a real position, that evolves deterministically under a non-local guiding equation. The evolution of a physical system is given at all times by the Schrödinger equation together with the guiding equation. There is never a collapse of the wave function. This solves the measurement problem. 52 Everett's many worlds interpretation, formulated in 1956, holds that all the possibilities described by quantum theory simultaneously occur in a multiverse composed of mostly independent parallel universes. 53 This is a consequence of removing the axiom of the collapse of the wave packet. All possible states of the measured system and the measuring apparatus, together with the observer, are present in a real physical quantum superposition. While the multiverse is deterministic, we perceive non-deterministic behavior governed by probabilities, because we do not observe the multiverse as a whole, but only one parallel universe at a time. Exactly how this is supposed to work has been the subject of much debate. Several attempts have been made to make sense of this and derive the Born rule. 54-55 with no consensus on whether they have been successful. 56-57-58 Relational quantum mechanics appeared in the late 1990s as a modern derivative of Copenhagen-type ideas. 59 and Cubism was developed some years later. 60 History Main articles, History of Quantum Mechanics and Atomic Theory. Max Planck is considered the father of the quantum theory. Quantum mechanics was developed in the early decades of the 20th century, driven by the need to explain phenomena that, in some cases, had been observed in earlier times. Scientific inquiry into the wave nature of light began in the 17th and 18th centuries, when scientists such as Robert Hooke, Christian Huygens, and Leonard Euler proposed a wave theory of light based on experimental observations. 61 In 1803 English polymath Thomas Young described the famous double-slit experiment. 62 This experiment played a major role in the general acceptance of the wave theory of light. During the early 19th century, chemical research by John Dalton and Amadeo Avogadro lent weight to the atomic theory of matter, an idea that James Clerk Maxwell, Ludwig Boltzmann, and others built upon to establish the kinetic theory of gases. The successes of kinetic theory gave further credence to the idea that matter is composed of atoms, yet the theory also had shortcomings that would only be resolved by the development of quantum mechanics. 63 While the early conception of atoms from Greek philosophy had been that they were indivisible units, the word atom deriving from the Greek for uncuttable, the 19th century saw the formulation of hypotheses about subatomic structure. One important discovery in that regard was Michael Faraday's 1838 observation of a glow caused by an electrical discharge inside a glass tube containing gas at low pressure. Julius Plucker, Johann Wilhelm Hittorf and Eugen Goldstein carried on and improved upon Faraday's work, leading to the identification of cathode rays, which J. Thomson found to consist of subatomic particles that would be called electrons. 64-65 The blackbody radiation problem was discovered by Gustav Kirchhoff in 1859. In 1900, Max Planck proposed the hypothesis that energy is radiated and absorbed in discrete quanta, or energy packets, yielding a calculation that precisely matched the observed patterns of blackbody radiation. 66 The word quantum derives from the Latin, meaning how great or how much. 67 According to Planck, quantities of energy could be thought of as divided into elements whose size, E, would be proportional to their frequency, nu equals, where h is Planck's constant. Planck cautiously insisted that this was only an aspect of the processes of absorption and emission of radiation and was not the physical reality of the radiation. 68 In fact, he considered his quantum hypothesis a mathematical trick to get the right answer rather than a sizable discovery. 69 However, in 1905 Albert Einstein interpreted Planck's quantum hypothesis realistically and used it to explain the photoelectric effect, in which shining light on certain materials can eject electrons from the material. Niels Bohr then developed Planck's ideas about radiation into a model of the hydrogen atom that successfully predicted the spectral lines of hydrogen. 70 Einstein further developed this idea to show that an electromagnetic wave such as light could also be described as a particle, later called the photon, with a discrete amount of energy that depends on its frequency. 71 In his paper on the quantum theory of radiation, Einstein expanded on the interaction between energy and matter to explain the absorption and emission of energy by atoms. Although overshadowed at the time by his general theory of relativity, this paper articulated the mechanism underlying the stimulated emission of radiation. 72 Which became the basis of the laser. The 1927 Solvay Conference in Brussels was the fifth World Physics Conference. This phase is known as the Old Quantum Theory. Never complete or self-consistent, the old quantum theory was rather a set of heuristic corrections to classical mechanics. 73 The theory is now understood as a semi-classical approximation. 74 To modern quantum mechanics. 75 Notable results from this period include, in addition to the work of Planck, Einstein, and Bohr mentioned above, Einstein and Peter Debye's work on the specific heat of solids, Bohr and Hendrika Johanna van Leeuwen's proved that classical physics cannot account for diamagnetism, and Arnold Sommerfeld's extension of the Bohr model to include special relativistic effects. In the mid-1920s, quantum mechanics was developed to become the standard formulation for atomic physics. In 1923, the French physicist Louis de Broglie put forward his theory of matter waves by stating that particles can exhibit wave characteristics and vice versa. Building on de Broglie's approach, modern quantum mechanics was born in 1925, when the German physicists Werner Heisenberg, Max Born, and Pascual Jordan 76-77 developed matrix mechanics, and the Austrian physicist Erwin Schrödinger invented wave mechanics. Born introduced the probabilistic interpretation of Schrödinger's wave function in July 1926. 78 Thus, the entire field of quantum physics emerged, leading to its wider acceptance at the Fifth Solvay Conference in 1927-79. By 1930, quantum mechanics had been further unified and formalized by David Hilbert, Paul Dirac, and John von Neumann. 80 With greater emphasis on measurement, the statistical nature of our knowledge of reality, and philosophical speculation about the observer. It has since permeated many disciplines, including quantum chemistry, quantum electronics, quantum optics, and quantum information science. It also provides a useful framework for many features of the modern periodic table of elements, and describes the behaviors of atoms during chemical bonding and the flow of electrons in computer semiconductors, and therefore plays a crucial role in many modern technologies. While quantum mechanics was constructed to describe the world of the very small, it is also needed to explain some macroscopic phenomena such as superconductors. 81 and superfluids. 82.
Well, that was a nice long read. Shall we read some more?
Top, History Observational Astrophysics Theoretical Astrophysics Popularization. See also references. Further reading. External links. Astrophysics article. Talk, read, edit, view. History tools from Wikipedia, the free encyclopedia. This article is about the use of physics to determine the nature of astronomical objects. For the use of physics to determine their positions and motions, see celestial mechanics. For the physical study of the largest scale structures of the universe, see physical cosmology. For the journal, see Astrophysics, Journal. Early 1900s comparison of elemental, solar, and stellar spectra. Part of a series on physics. The Fundamental Science Index. Outline. Glossary. History, Timeline, Branches. Research. Physics portal. Category Vitae. Astrophysics is a science that employs the methods and principles of physics and chemistry in the study of astronomical objects and phenomena. 1-2 As one of the founders of the discipline, James Keeler, said, astrophysics seeks to ascertain the nature of the heavenly bodies, rather than their positions or motions in space, what they are, rather than where they are. 3 Among the subjects studied are the Sun, solar physics, other stars, galaxies, extrasolar planets, the interstellar medium and the cosmic microwave background. 4-5 Emissions from these objects are examined across all parts of the electromagnetic spectrum, and the properties examined include luminosity, density, temperature, and chemical composition. Because astrophysics is a very broad subject, astrophysicists apply concepts and methods from many disciplines of physics, including classical mechanics, electromagnetism, statistical mechanics, thermodynamics, quantum mechanics, relativity, nuclear and particle physics, and atomic and molecular physics. In practice, modern astronomical research often involves a substantial amount of work in the realms of theoretical and observational physics. Some areas of study for astrophysicists include their attempts to determine the properties of dark matter, dark energy, black holes, and other celestial bodies, and the origin and ultimate fate of the universe. 4 Topics also studied by theoretical astrophysicists include solar system formation and evolution, stellar dynamics and evolution, galaxy formation and evolution, magnetohydrodynamics, large-scale structure of matter in the universe, origin of cosmic rays, general relativity, special relativity, quantum and physical cosmology, including string cosmology and astroparticle physics. History. Astronomy is an ancient science, long separated from the study of terrestrial physics. In the Aristotelian worldview, bodies in the sky appeared to be unchanging spheres whose only motion was uniform motion in a circle, while the earthly world was the realm which underwent growth and decay and in which natural motion was in a straight line and ended when the moving object reached its goal. Consequently, it was held that the celestial region was made of a fundamentally different kind of matter from that found in the terrestrial sphere, either fire as maintained by Plato, or ether as maintained by Aristotle. 6-7 During the 17th century, natural philosophers such as Galileo 8, Descartes 9 and Newton 10 began to maintain that the celestial and terrestrial regions were made of similar kinds of material and were subject to the same natural laws. 11 Their challenge was that the tools had not yet been invented with which to prove these assertions. 12 For much of the 19th century, astronomical research was focused on the routine work of measuring the positions and computing the motions of astronomical objects. 13-14 A new astronomy, soon to be called astrophysics, began to emerge when William Hyde Wollaston and Joseph von Fraunhofer independently discovered that, when decomposing the light from the sun, a multitude of dark lines, regions where there was less or no light, were observed in the spectrum. 15 By 1860 the physicist, Gustav Kirchhoff, and the chemist, Robert Bunsen, had demonstrated that the dark lines in the solar spectrum corresponded to bright lines in the spectra of known gases. Specific lines corresponding to unique chemical elements. 16 Kirchhoff deduced that the dark lines in the solar spectrum are caused by absorption by chemical elements in the solar atmosphere. 17 In this way it was proved that the chemical elements found in the Sun and stars were also found on Earth. Among those who extended the study of solar and stellar spectra was Norman Lockyer, who in 1868 detected radiant, as well as dark lines in solar spectra. Working with chemist Edward Franklin to investigate the spectra of elements at various temperatures and pressures, he could not associate a yellow line in the solar spectrum with any known elements. He thus claimed the line represented a new element, which was called helium, after the Greek Helios, the sun personified. 1819. In 1885, Edward C. Pickering undertook an ambitious program of stellar spectral classification at Harvard College Observatory, in which a team of woman computers, notably Williamina Fleming, Antonia Mori, and Annie Jump Cannon, classified the spectra recorded on photographic plates. By 1890, a catalogue of over 10,000 stars had been prepared that grouped them into 13 spectral types. Following Pickering's vision, by 1924 Cannon expanded the catalogue to 9 volumes and over 250,000 stars, developing the Harvard classification scheme, which was accepted for worldwide use in 1922-20. In 1895, George Ellery Hale and James E. Keeler, along with a group of 10 associate editors from Europe and the United States, 21 established the Astrophysical Journal, an international review of spectroscopy and astronomical physics. 22 It was intended that the journal would fill the gap between journals in astronomy and physics, providing a venue for publication of articles on astronomical applications of the spectroscope, on laboratory research closely allied to astronomical physics, including wavelength determinations of metallic and gaseous spectra and experiments on radiation and absorption, on theories of the sun, moon, planets, comets, meteors, and nebulae, and on instrumentation for telescopes and laboratories. 21 Around 1920, following the discovery of the Hertzsprung-Russell diagram still used as the basis for classifying stars and their evolution, Arthur Eddington anticipated the discovery and mechanism of nuclear fusion processes in stars, in his paper The Internal Constitution of the Stars. 23-24 At that time, the source of stellar energy was a complete mystery. Eddington correctly speculated that the source was fusion of hydrogen into helium, liberating enormous energy according to Einstein's equation E=mc2. This was a particularly remarkable development since at that time fusion and thermonuclear energy, and even that stars are largely composed of hydrogen, see metallicity, had not yet been discovered. 25 In 1925 Cecilia Helena Payne, later Cecilia Payne-Gaposchkin, wrote an influential doctoral dissertation at Radcliffe College, in which she applied ionization theory to stellar atmospheres to relate the spectral classes to the temperature of stars. 26 Most significantly, she discovered that hydrogen and helium were the principal components of stars. Despite Eddington's suggestion, this discovery was so unexpected that her dissertation readers convinced her to modify the conclusion before publication. However, later research confirmed her discovery. 27 By the end of the 20th century, studies of astronomical spectra had expanded to cover wavelengths extending from radio waves through optical, X-ray, and gamma wavelengths. 28 In the 21st century, it further expanded to include observations based on gravitational waves. Observational astrophysics supernova remnant LMC N63A imaged in X-ray, blue, optical, green, and radio, red, wavelengths. The X-ray glow is from material heated to about 10 million degrees Celsius by a shock wave generated by the supernova explosion. Observational astronomy is a division of the astronomical science that is concerned with recording and interpreting data, in contrast with theoretical astrophysics, which is mainly concerned with finding out the measurable implications of physical models. It is the practice of observing celestial objects by using telescopes and other astronomical apparatus. The majority of astrophysical observations are made using the electromagnetic spectrum. Radio astronomy studies radiation with a wavelength greater than a few millimeters. Example areas of study are radio waves, usually emitted by cold objects such as interstellar gas and dust clouds, the cosmic microwave background radiation, which is the redshifted light from the Big Bang, pulsars, which were first detected at microwave frequencies. The study of these waves requires very large radio telescopes. Infrared astronomy studies radiation with a wavelength that is too long to be visible to the naked eye but is shorter than radio waves. Infrared observations are usually made with telescopes similar to the familiar optical telescopes. Objects colder than stars, such as planets, are normally studied at infrared frequencies. Optical astronomy was the earliest kind of astronomy. Telescopes paired with a charge-coupled device or spectroscopes are the most common instruments used. The Earth's atmosphere interferes somewhat with optical observations, so adaptive optics and space telescopes are used to obtain the highest possible image quality. In this wavelength range, stars are highly visible, and many chemical spectra can be observed to study the chemical composition of stars, galaxies, and nebulae. Ultraviolet, X-ray and gamma-ray astronomy study very energetic processes such as binary pulsars, black holes, magnetars, and many others. These kinds of radiation do not penetrate the Earth's atmosphere well. There are two methods in use to observe this part of the electromagnetic spectrum: space-based telescopes and ground-based imaging air Cherenkov telescopes, IACT. Examples of observatories of the first type are RXTE, the Chandra X-ray Observatory and the Compton Gamma Ray Observatory. Examples of IACTs are the High Energy Stereoscopic System, HESS, and the MAGIC Telescope. Other than electromagnetic radiation, few things may be observed from the Earth that originate from great distances. A few gravitational wave observatories have been constructed, but gravitational waves are extremely difficult to detect. Neutrino observatories have also been built, primarily to study the Sun. Cosmic rays consisting of very high-energy particles can be observed hitting the Earth's atmosphere. Observations can also vary in their time scale. Most optical observations take minutes to hours, so phenomena that change faster than this cannot readily be observed. However, historical data on some objects is available, spanning centuries or millennia. On the other hand, radio observations may look at events on a millisecond time scale, millisecond pulsars, or combine years of data, pulsar deceleration studies. The information obtained from these different timescales is very different. The study of the Sun has a special place in observational astrophysics. Due to the tremendous distance of all other stars, the Sun can be observed in a kind of detail unparalleled by any other star. Understanding the Sun serves as a guide to understanding of other stars. The topic of how stars change, or stellar evolution, is often modeled by placing the varieties of star types in their respective positions on the Hertzsprung-Russell diagram, which can be viewed as representing the state of a stellar object, from birth to destruction. Theoretical astrophysics. See also, theoretical astronomy. Theoretical astrophysicists use a wide variety of tools which include analytical models, for example, polytropes to approximate the behaviors of a star, and computational numerical simulations. Each has some advantages. Analytical models of a process are generally better for giving insight into the heart of what is going on. Numerical models can reveal the existence of phenomena and effects that would otherwise not be seen. 29-30 Theorists in astrophysics endeavor to create theoretical models and figure out the observational consequences of those models. This helps allow observers to look for data that can refute a model or help in choosing between several alternate or conflicting models. Theorists also try to generate or modify models to take into account new data. In the case of an inconsistency, the general tendency is to try to make minimal modifications to the model to fit the data. In some cases, a large amount of inconsistent data over time may lead to total abandonment of a model. Topics studied by theoretical astrophysicists include stellar dynamics and evolution, galaxy formation and evolution, magnetohydrodynamics, large-scale structure of matter in the universe, origin of cosmic rays, general relativity and physical cosmology, including string cosmology and astroparticle physics. Relativistic astrophysics serves as a tool to gauge the properties of large-scale structures for which gravitation plays a significant role in physical phenomena investigated, and as the basis for black hole, astrophysics and the study of gravitational waves. Some widely accepted and studied theories and models in astrophysics, now included in the Lambda CDM model, are the Big Bang, cosmic inflation, dark matter, dark energy, and fundamental theories of physics. Popularization. The roots of astrophysics can be found in the 17th century emergence of a unified physics, in which the same laws applied to the celestial and terrestrial realms. 11 There were scientists who were qualified in both physics and astronomy who laid the firm foundation for the current science of astrophysics. In modern times, students continue to be drawn to astrophysics due to its popularization by the Royal Astronomical Society and notable educators such as prominent professors Lawrence Krauss, Subramanian Chandrasekhar, Stephen Hawking, Hubert Reeves, Carl Sagan and Patrick Moore. The efforts of the early, late, and present scientists continue to attract young people to study the history and science of astrophysics. 31, 32, 33 The television sitcom show The Big Bang Theory popularized the field of astrophysics with the general public, and featured some well-known scientists like Stephen Hawking and Neil deGrasse Tyson. See also astrochemistry, study of molecules in the universe and their reactions. Astronomical observatories. Astronomical spectroscopy, study of astronomy using spectroscopy to measure the spectrum of electromagnetic radiation. Astroparticle physics, branch of particle physics. Gravitational wave astronomy, branch of astronomy using gravitational waves. Hertzsprung, Russell diagram, scatter plot of stars showing the relationship of luminosity to stellar classification. High energy astronomy, study of astronomical objects that release electromagnetic radiation of highly energetic wavelengths. Important publications in astrophysics. List of astronomers, includes astrophysicists, neutrino astronomy, observing low-mass stellar particles. Timeline of gravitational physics and relativity. Timeline of knowledge about galaxies, clusters of galaxies, and large-scale structure. Timeline of human understanding of large-scale structures in space. Timeline of white dwarfs, neutron stars, and supernovae. Chronological list of developments in knowledge and records. Black hole article talk read view source view history tools from Wikipedia. Black hole article talk read view source view history tools from Wikipedia. Hole. Black hole article talk read view source view history tools from Wikipedia, the free encyclopedia, redirected from black hole. For other uses, see black hole, disambiguation. Direct image of a supermassive black hole at the core of MESI 87-1 animated simulation of a Schwarzschild black hole with a galaxy passing behind. Around the time of alignment, extreme gravitational lensing of the galaxy is observed. A black hole is a region of space-time where gravity is so strong that nothing, including light or other electromagnetic waves, has enough energy to escape it. The theory of general relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. 3. The boundary of no escape is called the event horizon. Although it has a great effect on the fate and circumstances of an object crossing it, it has no locally detectable features according to general relativity. 5. In many ways, a black hole acts like an ideal black body, as it reflects no light. 6. 7. Moreover, quantum field theory in curved space-time predicts that event horizons emit Hawking radiation, with the same spectrum as a black body of a temperature inversely proportional to its mass. This temperature is of the order of billionths of a Kelvin for stellar black holes, making it essentially impossible to observe directly. Objects whose gravitational fields are too strong for light to escape were first considered in the 18th century by John Michell and Pierre-Simon Laplace. 8. In 1916, Karl Schwarzschild found the first modern solution of general relativity that would characterize a black hole. David Finkelstein, in 1958, first published the interpretation of black hole as a region of space from which nothing can escape. Black holes were long considered a mathematical curiosity. It was not until the 1960s that theoretical work showed they were a generic prediction of general relativity. The discovery of neutron stars by Jocelyn Bell Burnell in 1967 sparked interest in gravitationally collapsed compact objects as a possible astrophysical reality. The first black hole known was Cygnus X1, identified by several researchers independently in 1971. 9-10 Black holes of stellar mass form when massive stars collapse at the end of their life cycle. After a black hole has formed, it can grow by absorbing mass from its surroundings. Supermassive black holes of millions of solar masses, m, may form by absorbing other stars and merging with other black holes. There is consensus that supermassive black holes exist in the centers of most galaxies. The presence of a black hole can be inferred through its interaction with other matter and with electromagnetic radiation such as visible light. Any matter that falls onto a black hole can form an external accretion disk heated by friction, forming quasars, some of the brightest objects in the universe. Stars passing too close to a supermassive black hole can be shredded into streamers that shine very brightly before being swallowed. 11 If other stars are orbiting a black hole, their orbits can be used to determine the black hole's mass and location. Such observations can be used to exclude possible alternatives such as neutron stars. In this way, astronomers have identified numerous stellar black hole candidates in binary systems and established that the radio source known as Sagittarius A*, at the core of the Milky Way galaxy, contains a supermassive black hole of about 4.3 million solar masses. History simulated view of a black hole in front of the Large Magellanic Cloud. Note the gravitational lensing effect, which produces two enlarged but highly distorted views of the cloud. Across the top, the Milky Way disk appears distorted into an arc. Published in 2019. 12 The idea of a body so big that even light could not escape was briefly proposed by English astronomical pioneer and clergyman John Michell in a letter published in November 1784. Michell's simplistic calculations assumed such a body might have the same density as the Sun, and concluded that one would form when a star's diameter exceeds the Sun's by a factor of 500, and its surface escape velocity exceeds the usual speed of light. Michell referred to these bodies as dark stars. 13 He correctly noted that such supermassive but non-radiating bodies might be detectable through their gravitational effects on nearby visible bodies. 8 14-15 Scholars of the time were initially excited by the proposal that giant but invisible dark stars might be hiding in plain view, but enthusiasm dampened when the wave-like nature of light became apparent in the early 19th century. 16 As if light were a wave rather than a particle. It was unclear what, if any, influence gravity would have on escaping light waves. 815 Modern physics discredits Mitchell's notion of a light ray shooting directly from the surface of a supermassive star, being slowed down by the star's gravity, stopping, and then free-falling back to the star's surface. 17 General relativity. See also, History of General Relativity plus lambda equals Introduction. History. Timeline. Tests. Mathematical formulation. Fundamental concepts. Phenomena. Kepler problem. Gravitational lensing. Gravitational waves. Frame drag. Geodetic effect. Event horizon. Singularity. Black hole. Space-time diagrams. Minkowski spacetime. Einstein, Rosen-Bridge equations. Formalism. Solutions. Scientists. Physics. Portal category. Veit. In 1915, Albert Einstein developed his theory of general relativity, having earlier shown that gravity does influence light's motion. Only a few months later, Karl Schwarzschild found a solution to the Einstein field equations that describes the gravitational field of a point mass and a spherical mass. 1819 A few months after Schwarzschild, Johannes Drost, a student of Hendrik Lorentz, independently gave the same solution for the point mass and wrote more extensively about its properties. 2021 The solution had a peculiar behavior at what is now called the Schwarzschild radius, where it became singular, meaning that some of the terms in the Einstein equations became infinite. The nature of this surface was not quite understood at the time. In 1924, Arthur Eddington showed that the singularity disappeared after a change of coordinates, although it took until 1933 for Georges Lemaître to realize that this meant the singularity at the Schwarzschild radius was a non-physical coordinate singularity. 22 Arthur Eddington did however comment on the possibility of a star with mass compressed to the Schwarzschild radius in a 1926 book, noting that Einstein's theory allows us to rule out overly large densities for visible stars like Betelgeuse because a star of 250 million kilometers radius could not possibly have so high a density as the Sun. Firstly, the force of gravitation would be so great that light would be unable to escape from it, the rays falling back to the star like a stone to the earth. Secondly, the redshift of the spectral lines would be so great that the spectrum would be shifted out of existence. Thirdly, the mass would produce so much curvature of the space-time metric that space would close up around the star, leaving us outside, i.e., nowhere. 2324 In 1931, Subramanian Chandrasekhar calculated, using special relativity, that a non-rotating body of electron-degenerate matter above a certain limiting mass, now called the Chandrasekhar limit at 1.4 m, has no stable solutions. 25 His arguments were opposed by many of his contemporaries like Eddington and Leif Landau, who argued that some yet unknown mechanism would stop the collapse. 26 They were partly correct. A white dwarf slightly more massive than the Chandrasekhar limit will collapse into a neutron star. 27 Which is itself stable. But in 1939, Robert Oppenheimer and others predicted that neutron stars above another limit, the Tolman, Oppenheimer, Fokoff limit, would collapse further for the reasons presented by Chandrasekhar, and concluded that no law of physics was likely to intervene and stop at least some stars from collapsing to black holes. 28 Their original calculations, based on the Pauli exclusion principle, gave it as 0.7 m. Subsequent consideration of neutron-neutron repulsion mediated by the strong force raised the estimate to approximately 1.5 m to 3.0 m. 29 Observations of the neutron star merger GW170817, which is thought to have generated a black hole shortly afterward, have refined the TOV limit estimate to 2.17 m. 30 31 32 33 34 Oppenheimer and his co-authors interpreted the singularity at the boundary of the Schwarzschild radius as indicating that this was the boundary of a bubble in which time stopped. This is a valid point of view for external observers, but not for infalling observers. Because of this property, the collapsed stars were called frozen stars, because an outside observer would see the surface of the star frozen in time at the instant where its collapse takes it to the Schwarzschild radius. 35 Golden Age. In 1958, David Finkelstein identified the Schwarzschild surface as an event horizon, a perfect unidirectional membrane. Causal influences can cross it in only one direction. 36 This did not strictly contradict Oppenheimer's results, but extended them to include the point of view of infalling observers. Finkelstein's solution extended the Schwarzschild solution for the future of observers falling into a black hole. A complete extension had already been found by Martin Kruskal, who was urged to publish at 37. These results came at the beginning of the golden age of general relativity, which was marked by general relativity and black holes becoming mainstream subjects of research. This process was helped by the discovery of pulsars by Jocelyn Bell Bernal in 1967-38-39, which, by 1969, were shown to be rapidly rotating neutron stars. 40 Until that time, neutron stars, like black holes, were regarded as just theoretical curiosities, but the discovery of pulsars showed their physical relevance and spurred a further interest in all types of compact objects that might be formed by gravitational collapse. Citation needed. In this period, more general black hole solutions were found. In 1963, Roy Kerr found the exact solution for a rotating black hole. 2 years later, Ezra Newman found the axisymmetric solution for a black hole that is both rotating and electrically charged. 41 Through the work of Werner Israel. 42 Brandon Carter. 43 44 and David Robinson. 45 The no-hair theorem emerged, stating that a stationary black hole solution is completely described by the three parameters of the Kerr-Newman metric: mass, angular momentum, and electric charge. 46 At first, it was suspected that the strange features of the black hole solutions were pathological artifacts from the symmetry conditions imposed, and that the singularities would not appear in generic situations. This view was held in particular by Vladimir Belinsky, Isaac Kalatnikov, and Yevgeny Lifshitz, who tried to prove that no singularities appear in generic solutions. However, in the late 1960s, Roger Penrose 47 and Stephen Hawking used global techniques to prove that singularities appear generically. 48 For this work, Penrose received half of the 2020 Nobel Prize in Physics, Hawking having died in 2018. 49 Based on observations in Greenwich and Toronto in the early 1970s, Cygnus X1, a galactic X-ray source discovered in 1964, became the first astronomical object commonly accepted to be a black hole. 50-51 Work by James Bardeen, Jacob Bekenstein, Carter, and Hawking in the early 1970s led to the formulation of black hole thermodynamics. 52 These laws describe the behavior of a black hole in close analogy to the laws of thermodynamics by relating mass to energy, area to entropy, and surface gravity to temperature. The analogy was completed when Hawking, in 1974, showed that quantum field theory implies that black holes should radiate like a black body with a temperature proportional to the surface gravity of the black hole, predicting the effect now known as Hawking radiation. 53 Observation on February 11, 2016, the LIGO Scientific Collaboration and the Virgo Collaboration announced the first direct detection of gravitational waves, representing the first observation of a black hole merger. 54 On 10 April 2019, the first direct image of a black hole and its vicinity was published, following observations made by the Event Horizon Telescope, EHT, in 2017 of the supermassive black hole in Messier 87's galactic center. 55 56 57 As of 2021. The nearest known body thought to be a black hole is around 1,500 light-years, 460 parsecs, away. Though only a couple dozen black holes have been found so far in the Milky Way, there are thought to be hundreds of millions, most of which are solitary and do not cause emission of radiation. 58 Therefore, they would only be detectable by gravitational lensing. Etymology: John Mitchell used the term dark star in a November 1783 letter to Henry Cavendish. 59 And in the early 20th century, physicists used the term gravitationally collapsed object. Science writer Marcia Bartusiak traces the term black hole to physicist Robert H. Dicke, who in the early 1960s reportedly compared the phenomenon to the Black Hole of Calcutta, notorious as a prison where people entered but never left alive. 60 The term black hole was used in print by Life and Science news magazines in 1963-60 and by science journalist Anne Ewing in her article Black Holes in Space, dated January 18, 1964, which was a report on a meeting of the American Association For the Advancement of Science held in Cleveland, Ohio 6162 in December 1967, a student reportedly suggested the phrase black hole at a lecture by John Wheeler. 61 Wheeler adopted the term for its brevity and advertising value. And it quickly caught on. 63 leading some to credit Wheeler with coining the phrase 64 properties and structure. Simple illustration of a non-spinning black hole. Artistic depiction of a black hole and its features. The no-hair theorem postulates that, once it achieves a stable condition after formation, a black hole has only three independent physical properties: mass, electric charge, and angular momentum. The black hole is otherwise featureless. If the conjecture is true, any two black holes that share the same values for these properties, or parameters, are indistinguishable from one another. The degree to which the conjecture is true for real black holes under the laws of modern physics is currently an unsolved problem. 46 These properties are special because they are visible from outside a black hole. For example, a charged black hole repels other like charges just like any other charged object. Similarly, the total mass inside a sphere containing a black hole can be found by using the gravitational analog of Gauss's law, through the ADM mass, far away from the black hole. 65 Likewise, the angular momentum, or spin, can be measured from far away using frame dragging by the gravitomagnetic field, through for example the lens, Thirring effect. 66 When an object falls into a black hole, any information about the shape of the object or distribution of charge on it is evenly distributed along the horizon of the black hole, and is lost to outside observers. The behavior of the horizon in this situation is a dissipative system that is closely analogous to that of a conductive stretchy membrane with friction and electrical resistance. The membrane paradigm. 67 This is different from other field theories such as electromagnetism, which do not have any friction or resistivity at the microscopic level, because they are time reversible. Because a black hole eventually achieves a stable state with only three parameters, there is no way to avoid losing information about the initial conditions. The gravitational and electric fields of a black hole give very little information about what went in. The information that is lost includes every quantity that cannot be measured far away from the black hole horizon, including approximately conserved quantum numbers such as the total baryon number and lepton number. This behavior is so puzzling that it has been called the black hole information loss paradox. 68-69 Gravitational time dilation around a black hole. Physical properties. The simplest static black holes have mass but neither electric charge nor angular momentum. These black holes are often referred to as Schwarzschild black holes after Karl Schwarzschild, who discovered the solution in 1916-19. According to Birkhoff's theorem, it is the only vacuum solution that is spherically symmetric. 70 This means there is no observable difference at a distance between the gravitational field of such a black hole and that of any other spherical object of the same mass. The popular notion of a black hole sucking in everything in its surroundings is therefore correct only near a black hole's horizon. Far away, the external gravitational field is identical to that of any other body of the same mass. 71 Solutions describing more general black holes also exist. Non-rotating charged black holes are described by the Reisner-Nordstrom metric, while the Kerr metric describes a non-charged rotating black hole. The most general stationary black hole solution known is the Kerr-Newman metric, which describes a black hole with both charge and angular momentum. 72 While the mass of a black hole can take any positive value, the charge and angular momentum are constrained by the mass. The total electric charge Q and the total angular momentum J are expected to satisfy the inequality 240 plus 222 less than or equal to 2 for a black hole of mass m. Black holes with the minimum possible mass satisfying this inequality are called extremal. Solutions of Einstein's equations that violate this inequality exist, but they do not possess an event horizon. These solutions have so-called naked singularities that can be observed from the outside, and hence are deemed unphysical. The cosmic censorship hypothesis rules out the formation of such singularities, when they are created through the gravitational collapse of realistic matter. 3 This is supported by numerical simulations. 73 Due to the relatively large strength of the electromagnetic force, black holes forming from the collapse of stars are expected to retain the nearly neutral charge of the star. Rotation, however, is expected to be a universal feature of compact astrophysical objects. The black hole candidate binary X-ray source GRS 1915 plus 10574 appears to have an angular momentum near the maximum allowed value. That unchanged arced limit is 75 less than or equal to 2, allowing definition of a dimensionless spin parameter such that 75 0 less than or equal to 2 less than or equal to 1. 75 Note 1 Black hole classifications. Class approximate. Mass approximate. Radius ultramassive black hole 109 to 1011 m greater than 1000 O supermassive black hole 106 to 109 m 0.001 to 400 O intermediate mass black hole 102 to 105 m 103 km R Earth stellar black hole 2 to 150 m 30 km micro black hole up to m Moon up to 0.1 mm Black holes are commonly classified according to their mass, independent of angular momentum, J. The size of a black hole, as determined by the radius of the event horizon, or Schwarzschild radius, is proportional to the mass, m, through s equals 222.95 km, where rs is the Schwarzschild radius and m is the mass of the Sunday 77 for a black hole with non-zero spin and / or electric charge. The radius is smaller. Note 2 until an extremal black hole could have an event horizon close to 78 plus equals 2. Event horizon. Main article. Event horizon. Far away from the black hole, a particle can move in any direction, as illustrated by the set of arrows. It is restricted only by the speed of light. Closer to the black hole, space-time starts to deform. There are more paths going towards the black hole than paths moving away. Note 3 inside of the event horizon, all paths bring the particle closer to the center of the black hole. It is no longer possible for the particle to escape. The defining feature of a black hole is the appearance of an event horizon, a boundary in space-time through which matter and light can pass only inward towards the mass of the black hole. Nothing, not even light, can escape from inside the event horizon. 8081 The event horizon is referred to as such because if an event occurs within the boundary, information from that event cannot reach an outside observer, making it impossible to determine whether such an event occurred. 82 As predicted by general relativity, the presence of a mass deforms space-time in such a way that the paths taken by particles bend towards the mass. 83 At the event horizon of a black hole, this deformation becomes so strong that there are no paths that lead away from the black hole. 84 To a distant observer, clocks near a black hole would appear to tick more slowly than those farther away from the black hole. 85 Due to this effect, known as gravitational time dilation, an object falling into a black hole appears to slow as it approaches the event horizon, taking an infinite time to reach it. 86 At the same time, all processes on this object slow down, from the viewpoint of a fixed outside observer, causing any light emitted by the object to appear redder and dimmer, an effect known as gravitational redshift. 87 Eventually, the falling object fades away until it can no longer be seen. Typically this process happens very rapidly, with an object disappearing from view within less than a second. 88 On the other hand, indestructible observers falling into a black hole do not notice any of these effects as they cross the event horizon. According to their own clocks, which appear to them to tick normally, they cross the event horizon after a finite time without noting any singular behavior. In classical general relativity, it is impossible to determine the location of the event horizon from local observations, due to Einstein's equivalence principle. 8990 The topology of the event horizon of a black hole at equilibrium is always spherical. Note 493 For non-rotating, static, black holes the geometry of the event horizon is precisely spherical, while for rotating black holes the event horizon is oblate. 94 95 96 Singularity. Main article. Gravitational singularity at the center of a black hole, as described by general relativity, may lie a gravitational singularity, a region where the space-time curvature becomes infinite. 97 For a non-rotating black hole, this region takes the shape of a single point. For a rotating black hole it is smeared out to form a ring singularity that lies in the plane of rotation. 98 In both cases, the singular region has zero volume. It can also be shown that the singular region contains all the mass of the black hole solution 99. The singular region can thus be thought of as having infinite density. 100 observers falling into a Schwarzschild black hole, i.e., non-rotating and not charged, cannot avoid being carried into the singularity once they cross the event horizon. They can prolong the experience by accelerating away to slow their descent, but only up to a limit 101. When they reach the singularity, they are crushed to infinite density and their mass is added to the total of the black hole. Before that happens, they will have been torn apart by the growing tidal forces in a process sometimes referred to as spaghettification or the noodle effect. 102 In the case of a charged, Reisner, Nordstrom, or rotating, Kerr, black hole, it is possible to avoid the singularity. Extending these solutions as far as possible reveals the hypothetical possibility of exiting the black hole into a different spacetime with the black hole acting as a wormhole. 103 The possibility of traveling to another universe is, however, only theoretical since any perturbation would destroy this possibility. 104 It also appears to be possible to follow closed time-like curves, returning to one's own past, around the Kerr singularity, which leads to problems with causality like the grandfather paradox. 105 It is expected that none of these peculiar effects would survive in a proper quantum treatment of rotating and charged black holes. 106 The appearance of singularities in general relativity is commonly perceived as signaling the breakdown of the theory. 107 This breakdown, however, is expected. It occurs in a situation where quantum effects should describe these actions, due to the extremely high density and therefore particle interactions. To date, it has not been possible to combine quantum and gravitational effects into a single theory, although there exist attempts to formulate such a theory of quantum gravity. It is generally expected that such a theory will not feature any singularities. 108-109 Photon sphere. Main article, Photon sphere. The photon sphere is a spherical boundary of zero thickness in which photons that move on tangents to that sphere would be trapped in a circular orbit about the black hole. For non-rotating black holes, the photon sphere has a radius 1.5 times the Schwarzschild radius. Their orbits would be dynamically unstable, hence any small perturbation, such as a particle of infalling matter, would cause an instability that would grow over time, either setting the photon on an outward trajectory causing it to escape the black hole, or on an inward spiral where it would eventually cross the event horizon. 110 While light can still escape from the photon sphere, any light that crosses the photon sphere on an inbound trajectory will be captured by the black hole. Hence any light that reaches an outside observer from the photon sphere must have been emitted by objects between the photon sphere and the event horizon. 110 For a Kerr black hole, the radius of the photon sphere depends on the spin parameter and on the details of the photon orbit, which can be prograde. The photon rotates in the same sense of the black hole spin, or retrograde. 111-112 Ergosphere. Main article, Ergosphere. The ergosphere is a region outside of the event horizon, where objects cannot remain in place. 113 Rotating black holes are surrounded by a region of space-time in which it is impossible to stand still, called the ergosphere. This is the result of a process known as frame dragging. General relativity predicts that any rotating mass will tend to slightly drag along the space-time immediately surrounding it. Any object near the rotating mass will tend to start moving in the direction of rotation. For a rotating black hole, this effect is so strong near the event horizon that an object would have to move faster than the speed of light in the opposite direction to just stand still. 114 The ergosphere of a black hole is a volume bounded by the black hole's event horizon and the ergosurface, which coincides with the event horizon at the poles but is at a much greater distance around the equator. 113 Objects and radiation can escape normally from the ergosphere. Through the Penrose process, objects can emerge from the ergosphere with more energy than they entered with. The extra energy is taken from the rotational energy of the black hole. Thereby the rotation of the black hole slows down. 115 A variation of the Penrose process in the presence of strong magnetic fields, the Blandford, Xeneject process is considered a likely mechanism for the enormous luminosity and relativistic jets of quasars and other active galactic nuclei. Innermost stable circular orbit, ISCO, main article, innermost stable circular orbit in Newtonian gravity, test particles can stably orbit at arbitrary distances from a central object. In general relativity, however, there exists an innermost stable circular orbit, often called the ISCO, for which any infinitesimal inward perturbations to a circular orbit will lead to spiraling into the black hole, and any outward perturbations will, depending on the energy, result in spiraling in, stably orbiting between apastron and periastron, or escaping to infinity. 116 The location of the ISCO depends on the spin of the black hole. In the case of a Schwarzschild black hole, spin 0 is ISCO equals 3 equals 62, and decreases with increasing black hole spin for particles orbiting in the same direction as the spin. 117 Formation and evolution. Given the bizarre character of black holes, it was long questioned whether such objects could actually exist in nature or whether they were merely pathological solutions to Einstein's equations. Einstein himself wrongly thought black holes would not form, because he held that the angular momentum of collapsing particles would stabilize their motion at some radius. 118 This led the general relativity community to dismiss all results to the contrary for many years. However, a minority of relativists continued to contend that black holes were physical objects. 119 And by the end of the 1960s, they had persuaded the majority of researchers in the field that there is no obstacle to the formation of an event horizon. 120 Simulation of two black holes colliding. Penrose demonstrated that once an event horizon forms, general relativity without quantum mechanics requires that a singularity will form within 47 shortly afterwards. Hawking showed that many cosmological solutions that describe the Big Bang have singularities without scalar fields or other exotic matter. Clarification needed. The Kerr solution, the No-Hair theorem, and the laws of black hole thermodynamics showed that the physical properties of black holes were simple and comprehensible, making them respectable subjects for research. 121 Conventional black holes are formed by gravitational collapse of heavy objects such as stars, but they can also in theory be formed by other processes. 122 123 Gravitational collapse. Main article, gravitational collapse. Gas cloud being ripped apart by black hole at the center of the Milky Way. Observations from 2006, 2010 and 2013 are shown in blue, green, and red, respectively. 124 Gravitational collapse occurs when an object's internal pressure is insufficient to resist the object's own gravity. For stars, this usually occurs either because a star has too little fuel left to maintain its temperature through stellar nucleosynthesis, or because a star that would have been stable receives extra matter in a way that does not raise its core temperature. In either case, the star's temperature is no longer high enough to prevent it from collapsing under its own weight. 125 The collapse may be stopped by the degeneracy pressure of the star's constituents, allowing the condensation of matter into an exotic denser state. The result is one of the various types of compact star. Which type forms depends on the mass of the remnant of the original star left if the outer layers have been blown away, for example, in a Type II supernova. The mass of the remnant, the collapsed object that survives the explosion, can be substantially less than that of the original star. Remnants exceeding 5 m are produced by stars that were over 20 m before the collapse. 125 If the mass of the remnant exceeds about 3 to 4 m, the Tolman, Oppenheimer, Fokoff limit 28, either because the original star was very heavy or because the remnant collected additional mass through accretion of matter, even the degeneracy pressure of neutrons is insufficient to stop the collapse. No known mechanism, except possibly quark degeneracy pressure, is powerful enough to stop the implosion, and the object will inevitably collapse to form a black hole. 125 Artist's impression of supermassive black hole seed. 126 The gravitational collapse of heavy stars is assumed to be responsible for the formation of stellar mass black holes. Star formation in the early universe may have resulted in very massive stars, which upon their collapse would have produced black holes of up to 103 m. These black holes could be the seeds of the supermassive black holes found in the centers of most galaxies. 127. It has further been suggested that massive black holes with typical masses of 105 m could have formed from the direct collapse of gas clouds in the young universe. 122. These massive objects have been proposed as the seeds that eventually formed the earliest quasars observed already at redshift 7. 128. Some candidates for such objects have been found in observations of the young universe. 122. While most of the energy released during gravitational collapse is emitted very quickly, an outside observer does not actually see the end of this process. Even though the collapse takes a finite amount of time from the reference frame of infalling matter, a distant observer would see the infalling material slow and halt just above the event horizon, due to gravitational time dilation. Light from the collapsing material takes longer and longer to reach the observer, with the light emitted just before the event horizon forms delayed an infinite amount of time. Thus the external observer never sees the formation of the event horizon. Instead, the collapsing material seems to become dimmer and increasingly redshifted, eventually fading away. 129. Primordial black holes and the Big Bang. Gravitational collapse requires great density. In the current epoch of the universe, these high densities are found only in stars, but in the early universe shortly after the Big Bang, densities were much greater, possibly allowing for the creation of black holes. High density alone is not enough to allow black hole formation, since a uniform mass distribution will not allow the mass to bunch up. In order for primordial black holes to have formed in such a dense medium, there must have been initial density perturbations that could then grow under their own gravity. Different models for the early universe vary widely in their predictions of the scale of these fluctuations. Various models predict the creation of primordial black holes ranging in size from a Planck mass equals /1.2 times 1019 GeV /c2 2.2 times 10^8 kg to hundreds of thousands of solar masses. 123. Despite the early universe being extremely dense, it did not recollapse into a black hole during the Big Bang, since the expansion rate was greater than the attraction. Following inflation theory, there was a net repulsive gravitation in the beginning until the end of inflation. Since then the Hubble flow was slowed by the energy density of the universe. Models for the gravitational collapse of objects of relatively constant size, such as stars, do not necessarily apply in the same way to rapidly expanding space such as the Big Bang. 130. High-energy collision simulated event in the CMS detector, a collision in which a micro-black hole may be created. Gravitational collapse is not the only process that could create black holes. In principle, black holes could be formed in high-energy collisions that achieve sufficient density. As of 2002, no such events have been detected, either directly or indirectly as a deficiency of the mass balance in particle accelerator experiments. 131. This suggests that there must be a lower limit for the mass of black holes. Theoretically, this boundary is expected to lie around the Planck mass, where quantum effects are expected to invalidate the predictions of general relativity. 132. This would put the creation of black holes firmly out of reach of any high-energy process occurring on or near the Earth. However, certain developments in quantum gravity suggest that the minimum black hole mass could be much lower. Some brainworld scenarios, for example, put the boundary as low as 1 TeV/c2. 133. This would make it conceivable for micro black holes to be created in the high-energy collisions that occur when cosmic rays hit the Earth's atmosphere, or possibly in the Large Hadron Collider at CERN. These theories are very speculative, and the creation of black holes in these processes is deemed unlikely by many specialists. 134. Even if micro black holes could be formed, it is expected that they would evaporate in about 10-25 seconds, posing no threat to the Earth. 135. Growth. Once a black hole has formed, it can continue to grow by absorbing additional matter. Any black hole will continually absorb gas and interstellar dust from its surroundings. This growth process is one possible way through which some supermassive black holes may have been formed, Although the formation of supermassive black holes is still an open field of research 127, a similar process has been suggested for the formation of intermediate mass black holes found in globular clusters. 136 black holes can also merge with other objects such as stars or even other black holes. This is thought to have been important, especially in the early growth of supermassive black holes, which could have formed from the aggregation of many smaller objects. 127 The process has also been proposed as the origin of some intermediate mass black holes. 138 Evaporation. Main article, Hawking radiation. In 1974, Hawking predicted that black holes are not entirely black but emit small amounts of thermal radiation at a temperature C3/8 pi gmkb, 53. This effect has become known as Hawking radiation. By applying quantum field theory to a static black hole background, he determined that a black hole should emit particles that display a perfect black body spectrum. Since Hawking's publication, many others have verified the result through various approaches. 139 If Hawking's theory of black hole radiation is correct, then black holes are expected to shrink and evaporate over time as they lose mass by the emission of photons and other particles. 53 The temperature of this thermal spectrum, Hawking temperature, is proportional to the surface gravity of the black hole, which, for a Schwarzschild black hole, is inversely proportional to the mass. Hence, large black holes emit less radiation than small black holes. 140 A stellar black hole of 1 m has a Hawking temperature of 62 nanokelvins. 141 This is far less than the 2.7 K temperature of the cosmic microwave background radiation. Stellar mass or larger black holes receive more mass from the cosmic microwave background than they emit through Hawking radiation and thus will grow instead of shrinking. 142 To have a Hawking temperature larger than 2.7 K, and be able to evaporate, a black hole would need a mass less than the Moon. Such a black hole would have a diameter of less than 1/10 of a millimeter. 143 If a black hole is very small, the radiation effects are expected to become very strong. A black hole with the mass of a car would have a diameter of about 1024 m and take a nanosecond to evaporate, during which time it would briefly have a luminosity of more than 200 times that of the Sun. Lower mass black holes are expected to evaporate even faster. For example, a black hole of mass 1 TeV/C2 would take less than 1088 seconds to evaporate completely. For such a small black hole, quantum gravity effects are expected to play an important role and could hypothetically make such a small black hole stable, although current developments in quantum gravity do not indicate this is the case. 145 The Hawking radiation for an astrophysical black hole is predicted to be very weak and would thus be exceedingly difficult to detect from Earth. A possible exception, however, is the burst of gamma rays emitted in the last stage of the evaporation of primordial black holes. Searches for such flashes have proven unsuccessful and provide stringent limits on the possibility of existence of low-mass primordial black holes. 146 NASA's Fermi Gamma Ray Space Telescope launched in 2008 will continue the search for these flashes. 147 If black holes evaporate via Hawking radiation, a solar mass black hole will evaporate, beginning once the temperature of the cosmic microwave background drops below that of the black hole, over a period of 1064 years. 148 A supermassive black hole with a mass of 1011 m will evaporate in around 2 times 10100 years. 149 Some monster black holes in the universe are predicted to continue to grow up to perhaps 1014 m during the collapse of superclusters of galaxies. Even these would evaporate over a timescale of up to 10,106 years. 148 Some models of quantum gravity predict modifications of the Hawking description of black holes. In particular, the evolution equations describing the mass loss rate and charge loss rate get modified. 150 Observational evidence by nature, black holes do not themselves emit any electromagnetic radiation other than the hypothetical Hawking radiation, so astrophysicists searching for black holes must generally rely on indirect observations. For example, a black hole's existence can sometimes be inferred by observing its gravitational influence on its surroundings. 151 On April 10, 2019, an image was released of a black hole, which is seen magnified because the light paths near the event horizon are highly bent. The dark shadow in the middle results from light paths absorbed by the black hole. 152 The image is in false color, as the detected light halo in this image is not in the visible spectrum, but radio waves. Artist's impression of the closest black hole to Earth and its Sun-like companion star. This artist's impression depicts the paths of photons in the vicinity of a black hole. The gravitational bending and capture of light by the event horizon is the cause of the shadow captured by the Event Horizon Telescope. The Event Horizon Telescope, EHT, is an active program that directly observes the immediate environment of black holes' event horizons, such as the black hole at the center of the Milky Way. In April 2017, EHT began observing the black hole at the center of MESSI 87-153. In all, 8 radio observatories on 6 mountains and 4 continents observed the galaxy in Virgo on and off for 10 days in April 2017 to provide the data yielding the image in April 2019. 154 After 2 years of data processing, EHT released the first direct image of a black hole, specifically, the supermassive black hole that lies in the center of the aforementioned galaxy. 155-156 What is visible is not the black hole, which shows as black because of the loss of all light within this dark region. Instead, it is the gases at the edge of the event horizon, displayed as orange or red, that define the black hole. 157 On May 12, 2022, the EHT released the first image of Sagittarius A*, the supermassive black hole at the center of the Milky Way galaxy. The published image displayed the same ring-like structure and circular shadow as seen in the M87* black hole, and the image was created using the same techniques as for the M87 black hole. However, the imaging process for Sagittarius A, which is more than 1,000 times smaller and less massive than M87, was significantly more complex because of the instability of its surroundings. 158 The image of Sagittarius A** was also partially blurred by turbulent plasma on the way to the galactic center, an effect which prevents resolution of the image at longer wavelengths. 159 The brightening of this material in the bottom half of the processed EHT image is thought to be caused by Doppler beaming, whereby material approaching the viewer at relativistic speeds is perceived as brighter than material moving away. In the case of a black hole, this phenomenon implies that the visible material is rotating at relativistic speeds, greater than 1000 km/s 2,200,000 miles per hour, the only speeds at which it is possible to centrifugally balance the immense gravitational attraction of the singularity, and thereby remain in orbit above the event horizon. This configuration of bright material implies that the EHT observed M87* from a perspective catching the black hole's accretion disk nearly edge-on, as the whole system rotated clockwise. 161. However, the extreme gravitational lensing associated with black holes produces the illusion of a perspective that sees the accretion disk from above. In reality, most of the ring in the EHT image was created when the light emitted by the far side of the accretion disk bent around the black hole's gravity well and escaped, meaning that most of the possible perspectives on M87* can see the entire disk, even that directly behind the shadow. In 2015, the EHT detected magnetic fields just outside the event horizon of Sagittarius A*, and even discerned some of their properties. The field lines that pass through the accretion disk were a complex mixture of ordered and tangled. Theoretical studies of black holes had predicted the existence of magnetic fields. 163 predicted appearance of a non-rotating black hole with toroidal ring of ionized matter, such as has been proposed. 164 as a model for Sagittarius A star. The asymmetry is due to the Doppler effect resulting from the enormous orbital speed needed for centrifugal balance of the powerful gravitational attraction of the hole. In April 2023, an image of the shadow of the MESSI 87 black hole and the related high-energy jet, viewed together for the first time, was presented 166 detection of gravitational waves from merging black holes on September 14, 2015. The LIGO Gravitational Wave Observatory made the first ever successful direct observation of gravitational waves 54,167. The signal was consistent with theoretical predictions for the gravitational waves produced by the merger of two black holes, one with about 36 solar masses, and the other around 29 solar masses. 54,168. This observation provides the most concrete evidence for the existence of black holes to date. For instance, the gravitational wave signal suggests that the separation of the two objects before the merger was just 350 kilometers, or roughly 4 times the Schwarzschild radius corresponding to the inferred masses. The objects must therefore have been extremely compact, leaving black holes as the most plausible interpretation. 54. More importantly, the signal observed by LIGO also included the start of the post-merger ringdown. The signal produced as the newly formed compact object settles down to a stationary state. Arguably, the ringdown is the most direct way of observing a black hole. 169. From the LIGO signal, it is possible to extract the frequency and damping time of the dominant mode of the ringdown. From these, it is possible to infer the mass and angular momentum of the final object, which match independent predictions from numerical simulations of the merger. 170. The frequency and decay time of the dominant mode are determined by the geometry of the photon sphere. Hence, observation of this mode confirms the presence of a photon sphere. However, it cannot exclude possible exotic alternatives to black holes that are compact enough to have a photon sphere. 169. The observation also provides the first observational evidence for the existence of stellar mass black hole binaries. Furthermore, it is the first observational evidence of stellar mass black holes weighing 25 solar masses or more. 171. Since then, many more gravitational wave events have been observed. 172. Proper motions of stars orbiting Sagittarius A*. The proper motions of stars near the center of our own Milky Way provide strong observational evidence that these stars are orbiting a supermassive black hole. 173. Since 1995, astronomers have tracked the motions of 90 stars orbiting an invisible object coincident with the radio source Sagittarius A star. By fitting their motions to Keplerian orbits, the astronomers were able to infer, in 1998, that a 2.6 times 106 m object must be contained in a volume with a radius of 0.02 light-years to cause the motions of those stars. 174. Since then, one of the stars called S2 has completed a full orbit. From the orbital data, astronomers were able to refine the calculations of the mass to 4.3 times 106 m and a radius of less than 0.002 light-years for the object causing the orbital motion of those stars. 173. The upper limit on the object's size is still too large to test whether it is smaller than its Schwarzschild radius. Nevertheless, these observations strongly suggest that the central object is a supermassive black hole, as there are no other plausible scenarios for confining so much invisible mass into such a small volume. 174. Additionally, there is some observational evidence that this object might possess an event horizon, a feature unique to black holes. 175. Accretion of matter. See also, accretion disk black hole with corona. X-ray source, artist's concept. 176. Due to conservation of angular momentum. 177. Gas falling into the gravitational well created by a massive object will typically form a disk-like structure around the object. Artists' impressions such as the accompanying representation of a black hole with corona commonly depict the black hole as if it were a flat space body hiding the part of the disk just behind it, but in reality gravitational lensing would greatly distort the image of the accretion disk. 178. NASA's simulated view from outside the horizon of a Schwarzschild black hole lit by a thin accretion disk. Within such a disk, friction would cause angular momentum to be transported outward, allowing matter to fall farther inward, thus releasing potential energy and increasing the temperature of the gas. 179. Blurring of X-rays near black hole, new STAR, August 12, 2014, 176 When the accreting object is a neutron star or a black hole, the gas in the inner accretion disk orbits at very high speeds because of its proximity to the compact object. The resulting friction is so significant that it heats the inner disk to temperatures at which it emits vast amounts of electromagnetic radiation, mainly X-rays. These bright X-ray sources may be detected by telescopes. This process of accretion is one of the most efficient energy-producing processes known. Up to 40% of the rest mass of the accreted material can be emitted as radiation. 179. In nuclear fusion, only about 0.7% of the rest mass will be emitted as energy. In many cases, accretion disks are accompanied by relativistic jets that are emitted along the poles, which carry away much of the energy. The mechanism for the creation of these jets is currently not well understood, in part due to insufficient data. 180 As such, many of the universe's more energetic phenomena have been attributed to the accretion of matter on black holes. In particular, active galactic nuclei and quasars are believed to be the accretion disks of supermassive black holes. 181 Similarly, X-ray binaries are generally accepted to be binary star systems in which one of the two stars is a compact object accreting matter from its companion. 181 It has also been suggested that some ultraluminous X-ray sources may be the accretion disks of intermediate mass black holes. 182 In November 2011, the first direct observation of a quasar accretion disk around a supermassive black hole was reported. 183 184 X-ray binaries. See also, X-ray binary computer simulation of a star being consumed by a black hole. The blue dot indicates the location of the black hole. This animation compares the X-ray heartbeats of GRS 1915 and IGRJ 17091, two black holes that ingest gas from companion stars. A Chandra X-ray observatory image of Cygnus X1, which was the first strong black hole candidate discovered. X-ray binaries are binary star systems that emit a majority of their radiation in the X-ray part of the spectrum. These X-ray emissions are generally thought to result when one of the stars, compact object, accretes matter from another, regular, star. The presence of an ordinary star in such a system provides an opportunity for studying the central object and to determine if it might be a black hole. 181 If such a system emits signals that can be directly traced back to the compact object, it cannot be a black hole. The absence of such a signal does, however, not exclude the possibility that the compact object is a neutron star. By studying the companion star, it is often possible to obtain the orbital parameters of the system and to obtain an estimate for the mass of the compact object. If this is much larger than the Tolman, Oppenheimer, Fokoff limit, the maximum mass a star can have without collapsing, then the object cannot be a neutron star and is generally expected to be a black hole. 181 The first strong candidate for a black hole, Cygnus X1, was discovered in this way by Charles Thomas Bolton. 185 Louise Webster, and Paul Murden. 186 In 1972 187 188 Some doubt, however, remained due to the uncertainties that result from the companion star being much heavier than the candidate black hole. Currently, better candidates for black holes are found in a class of X-ray binaries called soft X-ray transients. In this class of system, the companion star is of relatively low mass, allowing for more accurate estimates of the black hole mass. Moreover, these systems actively emit X-rays for only several months once every 10 to 50 years. During the period of low X-ray emission, called quiescence, the accretion disk is extremely faint, allowing detailed observation of the companion star during this period. One of the best such candidates is V404 Cygni 181 Quasi-periodic oscillations. Main article, Quasi-periodic oscillation. The X-ray emissions from accretion disks sometimes flicker at certain frequencies. These signals are called quasi-periodic oscillations and are thought to be caused by material moving along the inner edge of the accretion disk, the innermost stable circular orbit. As such, their frequency is linked to the mass of the compact object. They can thus be used as an alternative way to determine the mass of candidate black holes. 189 Galactic nuclei. See also, Active galactic nucleus magnetic waves, called Alfvén S waves, flow from the base of black hole jets. Astronomers use the term active galaxy to describe galaxies with unusual characteristics, such as unusual spectral line emission and very strong radio emission. Theoretical and observational studies have shown that the activity in these active galactic nuclei, AGN, may be explained by the presence of supermassive black holes, which can be millions of times more massive than stellar ones. The models of these AGN consist of a central black hole that may be millions or billions of times more massive than the Sun, a disk of interstellar gas and dust called an accretion disk, and two jets perpendicular to the accretion disk. 191 detection of unusually bright X-ray flare from Sagittarius A*, a black hole in the center of the Milky Way galaxy on 5 January 2015. 192 Although supermassive black holes are expected to be found in most AGN, only some galaxies' nuclei have been more carefully studied in attempts to both identify and measure the actual masses of the central supermassive black hole candidates. Some of the most notable galaxies with supermassive black hole candidates include the Andromeda Galaxy, M32, M87, NGC 3115, NGC 3377, NGC 4258, NGC 4889, NGC 1277, OJ 287, APM 08279 plus 5255 and the Sombrero Galaxy 193. It is now widely accepted that the center of nearly every galaxy, not just active ones, contains a supermassive black hole. 194 The close observational correlation between the mass of this hole and the velocity dispersion of the host galaxy's bulge, known as the M-sigma relation, strongly suggests a connection between the formation of the black hole and that of the galaxy itself. 195 Simulation of gas cloud after close approach to the black hole at the center of the Milky Way. 196 MICRO-lensing. Another way the black hole nature of an object may be tested is through observation of effects caused by a strong gravitational field in their vicinity. One such effect is gravitational lensing. The deformation of space-time around a massive object causes light rays to be deflected, such as light passing through an optic lens. Observations have been made of weak gravitational lensing, in which light rays are deflected by only a few arcseconds. MICRO-lensing occurs when the sources are unresolved and the observer sees a small brightening. In January 2022, astronomers reported the first possible detection of a MICRO-lensing event from an isolated black hole. 197 Another possibility for observing gravitational lensing by a black hole would be to observe stars orbiting the black hole. There are several candidates for such an observation in orbit around Sagittarius A star. 198 Alternative. See also, exotic star. The evidence for stellar black holes strongly relies on the existence of an upper limit for the mass of a neutron star. The size of this limit heavily depends on the assumptions made about the properties of dense matter. New exotic phases of matter could push up this bound. 181 A phase of free quarks at high density might allow the existence of dense quark stars. 199 And some supersymmetric models predict the existence of Q stars. 200 Some extensions of the Standard Model posit the existence of preons as fundamental building blocks of quarks and leptons, which could hypothetically form preon stars. 201 These hypothetical models could potentially explain a number of observations of stellar black hole candidates. However, it can be shown from arguments in general relativity that any such object will have a maximum mass. 181 Since the average density of a black hole inside its Schwarzschild radius is inversely proportional to the square of its mass, supermassive black holes are much less dense than stellar black holes. The average density of a 108 m black hole is comparable to that of water. 181 Consequently, the physics of matter forming a supermassive black hole is much better understood and the possible alternative explanations for supermassive black hole observations are much more mundane. For example, a supermassive black hole could be modeled by a large cluster of very dark objects. However, such alternatives are typically not stable enough to explain the supermassive black hole candidates. 181. The evidence for the existence of stellar and supermassive black holes implies that in order for black holes to not form, general relativity must fail as a theory of gravity, perhaps due to the onset of quantum mechanical corrections. A much anticipated feature of a theory of quantum gravity is that it will not feature singularities or event horizons, and thus black holes would not be real artifacts. 202. For example, in the fuzzball model based on string theory, the individual states of a black hole solution do not generally have an event horizon or singularity, but for a classical/semi-classical observer the statistical average of such states appears just as an ordinary black hole as deduced from general relativity. 203a. Few theoretical objects have been conjectured to match observations of astronomical black hole candidates identically or near identically, but which function via a different mechanism. These include the Grav-ASTA, the black star 204 and the dark energy star 205. Open questions: entropy and thermodynamics. Further information: black hole thermodynamics and Bekenstein bound S equals 1/4c3k/gha. The formula for the Bekenstein, Hawking entropy, S, of a black hole, which depends on the area of the black hole, A. The constants are the speed of light, c, the Boltzmann constant, k, Newton's constant, g, and the reduced Planck constant, h. In Planck units, this reduces to S equals A/4. In 1971, Hawking showed under general conditions note 5 that the total area of the event horizons of any collection of classical black holes can never decrease, even if they collide and merge. 206. This result, now known as the second law of black hole mechanics, is remarkably similar to the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease. As with classical objects at absolute zero temperature, it was assumed that black holes had zero entropy. If this were the case, the second law of thermodynamics would be violated by entropy-laden matter entering a black hole, resulting in a decrease in the total entropy of the universe. Therefore, Bekenstein proposed that a black hole should have an entropy, and that it should be proportional to its horizon area. 207. The link with the laws of thermodynamics was further strengthened by Hawking's discovery in 1974 that quantum field theory predicts that a black hole radiates blackbody radiation at a constant temperature. This seemingly causes a violation of the second law of black hole mechanics, since the radiation will carry away energy from the black hole, causing it to shrink. The radiation, however, also carries away entropy, and it can be proven under general assumptions that the sum of the entropy of the matter surrounding a black hole and 1/4 of the area of the horizon as measured in Planck units is in fact always increasing. This allows the formulation of the first law of black hole mechanics as an analog of the first law of thermodynamics, with the mass acting as energy, the surface gravity as temperature, and the area as entropy. 207. One puzzling feature is that the entropy of a black hole scales with its area rather than with its volume, since entropy is normally an extensive quantity that scales linearly with the volume of the system. This odd property led Gerard T. Hooft and Leonard Susskind to propose the holographic principle, which suggests that anything that happens in a volume of space-time can be described by data on the boundary of that volume. 208. Although general relativity can be used to perform a semi-classical calculation of black hole entropy, this situation is theoretically unsatisfying. In statistical mechanics, entropy is understood as counting the number of microscopic configurations of a system that have the same microscopic qualities, such as mass, charge, pressure, etc. Without a satisfactory theory of quantum gravity, one cannot perform such a computation for black holes. Some progress has been made in various approaches to quantum gravity. In 1995, Andrew Strominger and Cum Runvafa showed that counting the microstates of a specific supersymmetric black hole in string theory reproduced the Bekenstein, Hawking entropy. 209. Since then, Similar results have been reported for different black holes both in string theory and in other approaches to quantum gravity like loop quantum gravity 210. Another promising approach is constituted by treating gravity as an effective field theory. One first computes the quantum gravitational corrections to the radius of the event horizon of the black hole, then integrates over it to find the quantum gravitational corrections to the entropy as given by the Wald formula. The method was applied for Schwarzschild black holes by Calmette and Kuipers 211, then successfully generalized for charged black holes by Campos Delgado 212. Information loss paradox. Main article: Black hole information paradox. Unsolved problem in physics: is physical information lost in black holes? More unsolved problems in physics. Because a black hole has only a few internal parameters, most of the information about the matter that went into forming the black hole is lost. Regardless of the type of matter which goes into a black hole, it appears that only information concerning the total mass, charge, and angular momentum are conserved. As long as black holes were thought to persist forever, this information loss is not that problematic, as the information can be thought of as existing inside the black hole, inaccessible from the outside, but represented on the event horizon in accordance with the holographic principle. However, black holes slowly evaporate by emitting Hawking radiation. This radiation does not appear to carry any additional information about the matter that formed the black hole, meaning that this information appears to be gone forever. 213. The question whether information is truly lost in black holes, the black hole information paradox, has divided the theoretical physics community. In quantum mechanics, loss of information corresponds to the violation of a property called unitarity, and it has been argued that loss of unitarity would also imply violation of conservation of energy. 214. Though this has also been disputed. 215. Over recent years, evidence has been building that indeed information and unitarity are preserved in a full quantum gravitational treatment of the problem. 216. One attempt to resolve the black hole information paradox is known as black hole complementarity. In 2012, the firewall paradox was introduced with the goal of demonstrating that black hole complementarity fails to solve the information paradox. According to quantum field theory in curved spacetime, a single emission of Hawking radiation involves two mutually entangled particles. The outgoing particle escapes and is emitted as a quantum of Hawking radiation. The infalling particle is swallowed by the black hole. Assume a black hole formed a finite time in the past and will fully evaporate away in some finite time in the future. Then, it will emit only a finite amount of information encoded within its Hawking radiation. According to research by physicists like Don Page 217, 218 and Leonard Susskind, there will eventually be a time by which an outgoing particle must be entangled with all the Hawking radiation the black hole has previously emitted. This seemingly creates a paradox. A principle called monogamy of entanglement requires that, like any quantum system, the outgoing particle cannot be fully entangled with two other systems at the same time, yet here the outgoing particle appears to be entangled both with the infalling particle and, independently, with past Hawking radiation. 219. In order to resolve this contradiction, physicists may eventually be forced to give up one of three time-tested principles: Einstein's equivalence principle, unitarity, or local quantum field theory. One possible solution, which violates the equivalence principle, is that a firewall destroys incoming particles at the event horizon. 220. In general, which if any of these assumptions should be abandoned remains a topic of debate. 215.